So Fami is okay. You guys will watch this on YouTube tonight. Audio and whatever goes on the screen. Yeah, it's not camera. So you don't have to smile. Okay, here's what this one. I know a lot of you guys. We have a lot of journeymen here. If you guys start from the top, when you like you all know, when we have a power system coming to your building, you start with the utility transformer. This transformer right here most likely will be delta Y. Can you guys see that delta Y? Delta is the primary. So what I did, I assumed that we're going to have a service, electrical service transformer that's bringing 13.8 on the primary side. On the secondary side, we're taking 482.77. For all practical reasons, this could be a transformer that's bringing 7200 single phase and 24120 on the other side. For all the calculation I want to do, really it's the same. All the methods. So any question guys about this block here? That's my transformer. So delta Y, and I color code them based on what we typically do in the industry. So what the utility do, typically they go ground their neutral. Can you guys see that? This is now ground their neutral. Drive a ground rod right here. That's not within our jurisdiction. That's them. They do it. And to your building, it comes with these shaded things here, supposed to be conduits. Again, I'm not a graphic designer. I did as much as I could, guys. So that's supposed to be a conduit. So for us, really it starts with a conduit coming from the secondary of the transformer, as you can see, into so-called service point. We call it the service point, which is the CT cabinet or the meter socket. Or if you are doing residential, it will be at the top of the mast where you tie to your power, your overhead conductors coming. So here's my CT cabinet right in here. I want to bring your attention, guys, that we brought three-phase system with a neutral, the gray neutral with the 482.77 system. We're landing it phase A, B, and C in the CT cabinet, right? And we are at the CT cabinet, guys. What we do is we bond the CT. You are allowed by code to bond the neutral to the CT cabinet because you are on the line side of the disconnect means. Can you guys see this is little dot here or big dot here? Supposed to be you're grounding the box, the meter box, using what? The neutral. And that's allowed by code to ground the meter box using the neutral because the neutral is a grounded conductor too. So right here, and then so it is my meter socket. Then from my meter socket or CT cabinet, I brought another conduit, or it could be right next to my my transformer, and I brought the same thing, my three-phase and my neutral into the single most important one, which is a service equipment. That service equipment, I made it. It's not a panel board really. It's a switch gear, typically a switch gear, 4,000 amp, 482.77, and that's it's going to be our start point. This is a 4-wire system. You're bringing 3 phases and a neutral into a 4,000 amp switch gear, right? And you need to do grounding and bonding right at the service. Does that make sense? Right at the service, right in here. The meter socket, guys, we don't do the all grounding and bonding happen using the neutral. You can bond the meter socket using the neutral. So that's kind of how that goes. So here's my service equipment. I'm going to go over the big picture here. This is my service equipment. I number them. So these number, guys, correlate with the information in the second 2 pages that you guys got. Everybody understand that one? So that so here's number 1 is my neutral. How do you size a neutral? Because it's a grounding conductor. We'll go over that one. And then from my service equipment switch gear right here, that big 4,000 amp, I took a feeder, and as we always do, I took a feeder and I fed another panel in the same building. Can you guys see that one here? This is a 1,000 amp sub panel switch gear inside the same building. So we're going to do grounding and bonding for a sub panel. So we're going to do grounding and bonding at the service, then grounding and bonding at the sub panel. Can you guys see that right here? The one right underneath it is a sub panel, except it's a different building. So that will expose us, as you know, to grounding and bonding at separate building. What do you do when you have a separate building? You need to do grounding and bonding. So each one of these blocks, guys, I chose it intentionally because there is something special about it. You know, so I have the service feeding a sub panel in the same building, grounding and bonding as the sub panel. Then sub-panel in a different building, grounding and bonding. Then in the US, because we burn our receptacles at 120, you need almost always, I would say always, a transformer to take you from 480, 277 level to 288, 120, right? So I put a transformer here, and that will introduce us to the separated drive system, right? Grounding and bonding for separated drive system. That's very common. So that taking a feeder from here to a typically delta Y transformer, that my separated drive transformer right in here, and from the transformer we took a feeder to feed a separately derived panel, aka your receptacle panel, right? So that branch here, that feeder through the transformer, has a special grounding and bonding requirement. Don't you guys agree with that? So that's why I picked that particular scenario to do grounding and bonding for it. The last thing I have on this sheet is a generator. What happens if you have a backup generator or an emergency generator or legally required standby generator, and you need to do grounding and bonding for this generator? So when it comes to generator, guys, you have to make a decision. Are you running a separately derived system or non-separately derived system? So I'm going to go a little bit more in details when we talk about generators. Here's my gen, excuse me, and we're running my generators. So how do you bond and ground for a generator? This generator happened to be 1250 kW, but it could be a 50 kW sitting outside. It doesn't have to be 250. We made it 250 just to kind of get big feeders, so you can do calculation. And the system is 48277. So that's basically what this sheet is supposed to do, is taking a service panel and 3 feeders out of it. One feed a separate building, one feed a separate panel in the same building, and one feed a separately derived transformer that feed the receptacle panel in the same building. And we have a generator that we need to tie it to the system, and we need to do grounding and bonding for that system. Any comments, guys, about the big picture? Everybody can see what the... Now, in order to, if it looks complicated, it is, because we have to have 12 chapters in source book to reach that conclusion. Literally, these are summary of 12 chapters in 1 graphic and 2 pages with an example. So how to do the calculation at least. Any comments, guys, about how this is put together at least? So I'm gonna start, guys, by really focusing a little bit on right in here. So you saw the big picture. I'm going to focus a little bit on the service, right my service right in here. Right at the service, you bring in neutral. My neutral is coming with the 48377. You need to size a neutral. Why do we care about neutral when we talk about grounding and bonding? Because the neutral is a grounded conductor, right? Neutral is a grounded conductor, intentionally grounded conductor. So number 1, we'll give you guys how to size a neutral. I want to remind you my system is 4000 amp. This is how you size a neutral. So if you scroll down a little bit all the way here to number 1. Now I want to remind you we're doing number 1 here. Can you guys see number 1? Everybody goes to number 1. So the 2 pages after the graphic give you 2 things. Number 1 is, what's the name of this conductor? Is it grounded conductor, equipment grounding conductor, grounding electrode conductor, system bonding jumper, supply side bonding jumper? There's a lot of them. And where exactly it's located in the system, how do you size it, and where does it say that in the code? So you don't accuse me of pulling things from my basement, right? You always, if anybody asks you, where did you come up with this? Neil used to be all the time when he was in my class, come Chad, where did you find this in the code? Right? Because we all adhere to the code. So if you guys can see, the first column is the name of that conductor. This one happened to be conductor 1.0. There's really no reason why I call it 1.0 or 1. It just started with a grounded conductor. It's also neutral. I gave it the letter N, and it's at the service equipment. Does that, everybody knows how to read that one? The first column? You go to the second column, guys. It will tell you this is how you size it. You size it based on the power system unbalanced load. That's the most important thing. The neutral is always, you have to check the unbalanced loads. For example, you have an air handling unit, a chiller, rooftop unit. You have exhaust fans. All of them are 3-phase. Do these contribute to your neutral when you size your neutral? No. So all these big chunks of load, when you size your neutral at the service, what do you do with them? Throw them out as if they don't exist. So what exists when you size a neutral based on unbalanced load? Lighting system because it's running at 277 or 120. Receptacle because it's running at 120, right? Anything that have a neutral on it will count when you size neutral. Okay, now, to summarize this, long story short, if you size based on a neutral, you almost, the unbalanced load in a commercial and industrial building is, you almost always end up with a tiny, 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 tiny neutral conductor that the code does not allow you to use. If you try it, you can't. I mean, you can't, the code does not allow you to use. So, but you have to start with the unbalanced load. But this is what rules. What rules is not smaller than the main bonding jumper. That's what rules. The neutral conductor coming to your service will not, by code, not by me, be smaller than the main bonding jumper. Now we know how to calculate the main bonding jumper in a second. That's the one that's going to rule. Now, this third bullet says if paralleled in different raceways. If you decided to parallel in different raceways, and can anybody raise their hand and say, I brought feeders from a transformer to a 4,000 amp switchgear, and I put all the feeders in one conduit? Can you put all the feeders coming from 4,000 amp transformer into a 4,000 amp switchgear and put them in one conduit? There's no way you can do that. There's not enough conduit size. So what do you need to do when you do that size of a project? You need to parallel. If you parallel, the paralleling rule also applies, guys. You cannot, shall not, will not parallel less than what? 1 knot. So when you're sizing your neutral and you came up with number 2, but you're paralleling your neutral, can you use number 2? No, it has to go 1 knot. So that's why I threw this bullet, the third bullet. Any comments, guys? Any questions about that? Now, for the people who are like my friend Neil, they question me all the time, say, where did you get this junk, Chad? Here's your reference in an NEC code book. So that's where it tells you in an NEC code book, these 3 bullets. Does that make sense? Okay, now you have to dig a lot in source book to find that one and put them in. So what I thought, guys, when I came up with this is I want for my own. I wanted one sheet that put all the bonding and grounding together. You know what I mean? So if you have a project, you look at it and you say, oh, here's how I want to put it together. You know what I mean? And this is how you size it. Not, okay, how do we size the system bonding jumper? Every time you go, well, it's right there, and this is how you size it. Any comments, guys, about the neutral? Any comments about the neutral conductor here? So that's so I'm going to go to number 1. How do you size number 1, guys? We said it's based on the main bonding jumper. Okay, so it cannot be less than the main bonding jumper. And I have an example for you guys here. The main bonding jumper is size based. So let's go down to the main bonding jumper because we're talking about the main bonding jumper. So it cannot be less than the main bonding jumper. So main bonding jumper is right in here. Number 2, let's just go, as long as we're on it. So to size a neutral, the main bonding jumper rules. That's your bottom line. You can't go less than the main bonding jumper. So I'm going to go, guys, back and see what the heck is the main bonding jumper. The main bonding jumper in a switchgear is number 2. Can you guys see that? If your system is a grounded system, only if your system is a grounded system, meaning it's a delta grounded, solidly grounded system, you have to have a main bonding jumper where it takes your neutral conductor, tie it to your grounding electrode system, right? To stabilize the voltage, typically stabilize the voltage, and if you lose your neutral, the main bonding jumper, number 2 here, what happened if you lose your neutral, guys? What happened if you lose your neutral only? You have 3-phase, the 3-phase continue to pump power into your system, and you lost your neutral. You're running floating neutral, right? What happened if you have a floating neutral? In a 3-phase system, it's much easier than a single-phase system. The voltage is fluctuating, right? So some of them have more voltage, others have less voltage, so they start sharing the voltage based on their size. Long story short, you can burn equipment, literally. So that main bonding jumper, as you bond the neutral, it gives you another safety factor. If you were to lose your neutral right here, you can run forever on the ground. Not the code doesn't want you to do that, but if if you were to lose your neutral and your system is grounded and tied to the ground, you will stabilize the neutral at least. The neutral point would be stable. Okay, so here's my neutral. Here's my neutral bar in my switch gear. Here's my grounding bar in my switch gear. So what you do is you take a screw, tie the two together, right? Or you take a copper bar, tie the two together inside the switchgear, or you take a piece of wire and you tie them together. So that's your number 2, the main bonding jumper. Grounding your neutral. Any comments, guys? Any questions about that one? How many of you have done ungrounded system? If you've done a delta ungrounded system, then that number 2 does not exist. There is no number 2. Is there number 1 in an ungrounded system? If your system is ungrounded, is there number 1, the neutral? No. So number 1 and number 2, if you're running a delta system, they don't exist. Okay, so 90% of the time, guys, what we do, we run a grounded system as a service. So here's number 2, bonding the neutral to the ground. I'm going to go down to number 2 because that will help me into, here's number 2, main bonding jumper. Here's how you size it. The main bonding jumper, based on the service entrance conductor size. If service entrance conductors are parallel, multiply the number of sets by the service and conductor size. And oh, by the way, if you exceed 1100 kcm or 1750 aluminum, 1100 kcm copper or 1750 aluminum, you have to use the 12.5%. You don't believe, Chad? Where does it say that in the code? 250.28D1 and table 250.66. That's how you size the main bonding jumper. Cool. Okay, so let's go do that. Let's do that. That's how we size it. Let's go size it. Because when we size the main bonding jumper, guys, we find the neutral. That's why I started with that one. Okay, so I have an ungrounded. So I have a I want to remind you, we have a 4,000 amp switchgear. If they ask you to size feeders for a 4,000 amp switchgear, what do? You have to parallel. There's no way you can pull one conductor. There's no one conductor can carry 4,000 amps. So you parallel. How many sets you want to parallel? You know, I want to parallel 10 sets. Can you parallel 12? Yeah, you can parallel 12. So I chose to parallel 2 sets. So take the 4,000 amp, divided by 10, get you 400. Go to 310.15B16. She got married. She changed their name this year, 2011. Do you guys remember that? When she got married. So 310.15B16 under 75-degree column, and that will give you 10 sets of 3 conductors, number 600 kcm each. Done. Now, I'm sure a lot of you guys say we don't like 600 kcm, Chad. We're going to work with 500 or less, right? You can go parallel 2 sets, probably 12 or 11. You don't want to add numbers when you parallel. So if you take 12 sets, we'll get you probably, I think, 400 or something. So you can run 400. So I just did this example based on 600 kcm. Any comments, guys, about how we size the ungrounded conductor here? Everybody knows that. If you guys are a journeyman, you have done that in school, or it's not a big deal. Why do I care about the ungrounded conductor? Because based on the ungrounded conductor, I can size the main bonded jumper. So everything is interconnected, as you can tell. Okay, so now here's my 600 came from sizing the feeder. So I'm going to have 10 sets, literally 10 sets, 5, 5, going from the transformer into the seat, probably the CT cabinet, through the CT cabinet into the, or termination box into the switchgear. Then you take now to size the main bonding jumper, here's what it says, guys. You have to multiply the parallel, the service interconductor by how many sets you parallel. Okay, here's 10 of them, multiplied by 600 kcm each. Now, 10 times 600 is more than 1100 kcm, right? So you have to apply the bullet number 3. You can see the bullet number 3, which is 12.5%. So that's where the 12.5% came to be. You end up with 750 kcm. 750 kcm. Is 750 kcm a standard size? Because you could end up with a number that's not a standard size, right? So you're going to go check 700 kcm based on Chapter 9, Table 8. And yep, it is a standard size. The reason why I put the bottom one, because you end up a lot of times, guys, with a number that's not a standard size. So you're going to go where? Up to a standard size. Where do you find the standard sizes? One place is Chapter 9, Table 8. They're all there. There's also table, 310.15B16. So here's your 750 kcm. Any comments, guys? Any questions about that? So your main bonding jumper is going to be 750 kcm.
Could that be parallel?
Could that be parallel?
Yeah, you have to use one conductor.
Okay, very good point. When it comes to the main bonding jumper, so I'll get into this in one little second. Yes, it could be parallel too. You could, but I'll show you how to size them. That's this one. If you took Oh, you mean cut it by? Why would you do that? Because it's too big. It's too big.
Yeah.
Yeah, I don't think there's anything that says that I know of that says it cannot be parallel. It was too big. The reason, guys, why it's too big, because how often do you have a conductor to bond the neutral to the ground in the switch gear? What do they have? They have the copper bar, the bonding. I just use this one as a demo. You would never see this one in real life, because typically they have a big copper or aluminum bar that tying the two together. So you don't have to worry about this. But if you are to decide single-handedly to get rid of that one and put a conductor, but this is what this will help you. Then when you size the copper bar, that will be the manufacturer's UL. Then that will, they have their own rules, but that will be kind of a guide for sizing that copper bar if you have to. So, yeah, that's how they get around it, is having a copper bar, tying them together. Okay, any comments, guys, about number 2? Does it make sense? How to size number 2? Now, the reason why I started with this one, because I want to go to number 1. Now, here's where the main bonding, to get the neutral, the minimum has to be the main bonding jumper. So here's my main bonding jumper 750, but there's one little problem now. I'm paralleling it, right? So you take your 750, dividing them by 10. Why did I divide it by 10? Because you have 10 sets. You need one neutral with every set. You can't have the neutral with one set. So I divided the minimum size of the neutral divided by 10. So I came up with 750 kcm. If you take the 750 kcm to chapter 9, table 8 to get you number 1. What's wrong with number 1? Thank you, because we cannot parallel number 1, at least for power. For low voltage, believe it or not, you can. For low voltage. So you end up with minimum of 1 aught. 1 aught with each one of them. Can I go more than that 1 aught? Absolutely. 250? Absolutely. A lot of engineers, guys, pump it up a little bit, a step or two. But when you reach, the reason why it's so small, like you have a neutral of 1 aught and a phase of 600, because by the time you reach the 4000 amp switch gear, how much neutral load do you have, really? All your air handling units are gone, rooftop units gone, exhaust fans, chiller, all of them are 3-phase. No neutral contribute, they don't contribute to the neutral. So the only thing left is really your lights, the lights and receptacles inside your building. And I want to remind you, these are 1 aught each. So it's not just 1 aught for the neutral, 1 aught each. So they are more than 1 aught in reality. So, any question, guys, about number 1? Does that make sense? No? Do you guys do it differently? So that's as ugly as it gets in terms of the neutral. So we size the neutral, guys, and we size the main bonding jumper. The main bonding jumper right here. We size it. We size the neutral. There's one little tiny thing that they introduce is number 4. Now, so I'm going to go to number 1, number 2. I'm going to go directly. Let's go to number 3 in order. Number 3. Number 3 is your guys, is your grounding electrode conductor. The code says you are to establish a grounding electrode system at the building. A grounding electrode system can be one grounding electrode, the steel of the building. That's done. Catch 22. The code says if you have other qualified grounding electrode system in your area, you must use them. So long story short, you end up using tons of them. Okay, so number 3 is grounding electrode conductor. Okay, so I mind my graphic here, but this is supposed to be if you can use multiple of them, guys. As you know, you can have a ground rod. I don't know which one it was. Let's say that's a ground rod. You can use a ground ring. You can use a ground plate, right? You can use steel if you're building a steel. You can use a pipe, the water pipe, and I can't remember. That's a tank underground. It's buried underground tank. Qualify as a grounding electrode system. You only need one of them, but if others exist, you must bond to them. So what I thought is to have. I'm sure you guys are familiar with a grounding bar. What they do in a bigger system like this is on the wall they will have that copper grounding bar on the wall, and they bring all these grounding electrode system into that copper bar, tie it to it, and then they can ground the switch gear, the generator, the separated drive system. So that piece here, it gives you one single point where you can tie to the grounding electrode system external to the switch gear. You don't want to put it inside the switch gear, because say you want every time you want to tie a grounding electrode system to open the switch gear and tie to your switch gear. It's not a good idea. Any comments, guys, about this cover bar here? Sits.
Is there a size for the copper bar?
You're going to size it enough to handle your minimum size would be number 3, the one, or the largest. Your minimum size would be the largest grounding electrode conductor of the whole system, because I have generators there too. So the largest grounding electrode conductor, that will be your minimum size basically. But typically you have ample amount of room to put. Really, becomes the room is just to put your conductors in them. Okay, here's your number 3. So I'm going to go directly to number 3, guys, and I want to remind you number 3 has the main coming from the switch gear, and has also multiple. These are going to grounding electrode system, so-called grounding electrode system at the bottom. So if you go down here to number 3, let's go directly to number 3. Here's number 3. Number 3, guys, summarize it. It's called grounding electrode conductor. I always say when I start using the NEC code book, guys, I said the terminology is so important. You cannot call it grounding conductor, because grounding conductor is meaningless. You have to call it grounding electrode conductor. So that's what the code calls it. That's how you find it in the NEC code book. If you're sitting for a master exam, you can't just say the grounding conductor. This is the grounding electrode conductor. It takes the ground bar inside your switch gear into the grounding electrode system. What I did, I have a couple of bullets that I believe it's so important for you guys. I said first you size it based on the service entrance conductor. If you parallel, then you do the same thing, multiply by the number of sets. If service size is larger than this, can you guys see that? No larger than number 3 is needed. That's the difference between main bonding jumper and the grounding electrode conductor. If you end up with more than 1100 kcm or 1750, you don't have to go larger than number 3 out. You do not have to. Minimum of 1 grounding electrode connection. If other electrodes exist, you must tie to them. So I summarized the whole requirement, guys. And then if you connect to a rod, pipe, or a plate, you don't have to go more than number 6. That's directly to a rod. You don't have to go more than number 6, or a plate or a pipe. If you connect to concrete encased electrode, you don't have to go more than number 4. And if you have a ground ring, you don't have to go more than number 2, because your ground ring minimum is number 2. Unless your ground ring is 500 kcm, then you have to tie with 500 kcm, if you decided to go that route. So I summarized the whole thing here for you. Right in here, this is where it tells you all this this stuff. Then you come over here. Here's my 10 times 600 kcm, get you 6,000. You go to 250.66, and you get your 3/0, and you stop right there. That's the one that's going to the bar. This is the 3/0, and again, you can always go. The 3/0 is that conductor coming all the way here. Now, how about these little conductors here going tabbed into the grounding electrode system? These are your minimum. Again, I can't emphasize the word minimum. So if you go to, let's go to 3. Where am I here in 3? Here's my 3. The rod 6, pipe 6, plate 6, concrete 4, and ground ring 2. Minimum. Can I go more than that? Yes. Any comments? Any questions, guys? There are ground rings that people use 500 kcm around the building, engineered projects. So what you're seeing is the minimum. Any comment about the grounding electrode conductor and the main bonding jumper and the grounded conductor at the service? Make sense? No? Yes? So that's, and the red stuff is, like I said, is an example. I thought just to throw that one there. Okay, so moving on. So we sized, guys, the grounding electrode conductor. We sized the number 2, the main bonding jumper. Number 4 is the most confusing one. Number 4 here is called supply side bonding jumper. So as you bring your rigid metal conduit You bring your the 10 rigid metal conduit, and why rigid, Chad? Why not PVC? When you bring your rigid or intermediate or EMT, any metallic conduit, you're bringing it underground, typically rigid if you're going underground, into the bottom of the switchgear. As you know, the bottom of the switchgear is open. You need to bond your conduit to the switchgear, right? So that bonding the conduit to the switchgear is called supply side bonding jumper. Does that make sense? So how many of these number 4 do you think I'm going to have in my example? 10 of them, the way I'm showing them. Or you can have one and daisy chain them. Go from the first conduit to the second, to the third, to the fourth, to the 10th, and down into the ground bar inside the switchgear. So you have two methods. You either go pure conduit to the ground bar, or you can daisy chain them. If you daisy chain them, you size based on all the conductors put together. If you go from a conduit to the ground bar one at a time, then you size it based on only the conductor inside that conduit. That's the difference. Does that make sense, guys? So let's take the number 4 here. It's called supply side bonding jumper. Why it's supply side? Because supply side of the service disconnect means. Where do you think my service disconnect means is going to be located? Right inside the switchgear here. Okay, so let's go to number 4 if you guys don't mind. By the way, am I going too fast? I've been accused of having 2 speeds, fast and faster, right, Neil? So, so please stop me at any time. Okay, so number 4, the technical term for number 4, which is bonding the conduit, it's called supply side bonding jumper, SSBJ. And you don't have to do anything. See what the nice thing? You don't have to do any calculation because it cannot be smaller than the main bonding jumper. That's it. So what was the main bonding jumper for me? 750 kcm. Now that's if you daisy chain them. That's if you daisy chain them. If you don't daisy chain them, then you have to size it based on the conductors inside each conduit. So say, what size do you think it's going to be if we're not daisy chaining? 1, 2, 3 to 5. So I have 600 kcm. Can you guys go? Do you have your code book? Go to 250.66 and size for 600 kcm. Copper. We're all copper, right? Engineers love copper. They don't pay for it anyway, so. Why not? So here's your option. I either have a 1/0 from conduit to the ground bar, conduit ground bar. So I have 10 1/0s, or 1 750. Does that make sense? 10 1/0 or 1 750. So that's basically what that's called supply side bonding jumper. That's probably the most confusing one for a lot of people, guys. When the supply side, everybody knows the main bonding jumper and the grounding and the tow conductor. The supply side bonding jumper probably the most confusing one. Now, what happened, Chad, when we bring PVC? Do you need a supply side bonding jumper? No. Now, does the supply side bonding jumper need to be a wire? No. Take this. So you have a 200 amp and you're coming with your conduit rigid from the top, right, with the hub threaded. Where's your supply side bonding jumper? The hub itself is your supply side bonding jumper. Cool. Another example, you're coming for a 200 amp service, so you're coming with a rigid thread. If you're coming with rigid threaded with lock nuts on both sides tight, that's also qualify as the supply side bonding jumper. How about bonding bushing? You put a bonding bushing. That's the only time we need a bonding jumper. If you put a bonding bushing and with a wire and you tie it to the ground bar inside your switchgear, that's the only time you need supply side bonding jumper. There's options where you do not need a wire supply side bonding jumper because the wiring method, guys, qualify as a bonding the conduit into the switchgear. Does that make sense? Does that make sense? There's a couple of examples that there's also grounding wedge, where if the conduit, I want to remind you, this is bonding at the service. It's special bonding at the service. It's special bonding. So you have a service 200 amp, and you bring in an EMT conduit, and say and you need 2-inch, and the 2-inch match. There's no knockouts, right? There's no knockouts, nothing. And you bring it inside the EMT into the box, no knockouts. Then you can use a bonding wedge, or you can have a lockout, a connector that qualify as a bonding connector. So there's alternatives, multiple alternatives to the grounding bushing. Multiple alternatives to the grounding bushing. Grounding bushing, guys, become the only solution if you're coming to a bottom of a switch gear. How are you going to bond if you're coming open bottom of a switch gear? The only solution is to use a bonding bushing, bond all these conduits. Any comments, guys? Any questions about the supply side bonding jumper? Bonding the conduits. Bonding the conduits. So that's the bonding the conduits. So let me know how you guys want to take breaks. Do you want to take a break every hour like I usually do, or you want to? I don't know how. Typically every hour I give you 5 minutes break. Is that good to stretch and move on? Shall we? Let's take 5 minutes on the time. Thank you. So that's basically what I wanted to show you. I have since we're talking about the service, I thought to throw a couple of things about service and grounding conductors. There's a few things, guys, about the grounding conductor, but I want to go directly into my main bonding jumper, sizing the main bonding jumper. This is the information that we talked about. So this is just a couple of pictures, guys, about what your grounded conductor. You can see the picture for your grounding conductor versus a grounding electrode conductor tied together right at the service. The NEC code book says that you have to tie the grounded conductor to the service where the service disconnect mean reside. So a couple of nice picture on that one. Grounding electrode, different grounding electrode system. I'm just going to pick a few of these. We talked about the sizing. So this is another one, guys, about paralleling at the service. We talked about if you're paralleling, you can't go less than 1 aught. If you're paralleling conductor, you cannot go less than 1 aught for your grounded conductor, as well as everything else. So that's what I'm trying to see. I'm going to go directly into quick here to the main bonding. Okay, so here's main bonding jumper. I'm just going to show a couple of pictures, guys. I'll go over these. Here's an example of a main bonding jumper with a grounding electrode conductor and a grounding conductor in a panel, and I'm sure a lot of you guys have seen that many times. This is not a wire type. Here's a main bonding jumper. It doesn't have to be a 700. What was it? Ours was 700 kcm. Doesn't have to be 750 kcm. It could be a screw inside your panel, 100 or 200 amp panel. Here's another main bonding jumper, grounding electrode conductor. You can see grounding conductor, grounding electrode conductor, and a main bonding jumper. Inside the switch gear, this is what you typically see, and I'm sure you guys have done it. That's how you bond the neutral, the grounding electrode conductor into your neutral. So these are just, I thought, what I like about them is the picture, because they're much better than my pictures. Same thing, main bonding jumper. The idea is to bond your neutral to the enclosure where the disconnect is residing, as well as to the grounding electrode system right inside the service panel. Here's your main bonding jumper. This is my neutral bar bonded to the grounding electrode system and bonded to the enclosure. So that's kind of I thought just to show a few of these. I want to go a couple of these into, oh, here you go. I'm going to show supply side bonding jumper, because really nice pictures about supply side bonding jumper. We talked about supply side bonding jumper, guys. Here's how you size them. Like we said, one from each conduit, these rigid or EMT bonding bushing. That's, what did we come up with, 1/0, you said? 1/0 based on this example. The other example is daisy chain them. So you can see how they are all daisy chain now. Based on the daisy chain example that we did, that was 750. So that's your 750 daisy chain. And who wouldn't work with 750? Really, Chad? So in a situation like this, which option would you choose? You know what I mean? So it's so it'll be that option. No, why not, right? But because you don't want to work with 750. So that's, I thought, supply side bonding jumper. Here's another. If you parallel another supply side bonding jumper external, it doesn't have to be internal, right? Going across the flex, because the flex is not qualified as a bonding or equipment grounding conductor, as we all know. So you have to bond around it. So in a case like this, everybody knows, guys, that when you size when you size it, you're going to size things based on, and the conductor in this case is phase A, phase B, phase C. And let's just say that was a 600 kcm because we did it. Here's my 600 kcm in each one of them. KCM, 2 set parallel KCM, and then this guy in this case would be number 1/0, right? Is that what we did the example for it? The supply side bonding jumper. Any comments, guys? Any questions about that? Does it make sense though? The pictures makes it a little bit make more sense when you do it. Here's one method of bonding the conduit using a supply side bonding jumper. The reason why they call it supply side bonding jumper because it's at the service. It doesn't have to be this method. Here's a a couple of grounding at the service. Let's just go. I want to show a couple of. Here you go. Now, if you guys remember, we're bonding at the service. When we bond at the service, the best way of bonding at the service is to have a bonding bushing with, if you're smaller, a small panel. If you're a switch gear, you have a copper bar bonding the ground bar into the neutral bar directly inside your switch gear, done. You have a smaller panel, 100 amp panel, and you want to bond. The best method is to have a bonding bushing. You have your conductors tied to the bonding bushing and to the grounding bar inside your panel. That's the best way. But there are alternative, cheaper, easier alternative. Here's one of them, guys. So bonding lock knot. Bonding lock knots, again, that's also called system bonding jumper alternative. So you don't need a wire. The only restriction on this one, used where no concentric or eccentric knockouts remain. So the conduit match the hole. So in the case we're at the remember, we are at the service. Remind you, that's bonding at the service, not at the sub panel, not downstream. Here's an alternative for you. The other alternative is the wedge, guys, too. Same thing. Use where bonding jumper around concentric or eccentric knockouts. So if you don't have eccentric or concentric knockouts, these are two alternatives that you can use to the bonding jumper. These are also bonding lock knots for service approved to avoid having a bonding bushing with a supply side bonding conductor. Does that make sense, guys? The alternative that you can have. Here's the wedge that can get you an alternative to having that conductor that called supply side bonding jumper. We are at the service. I want to remind you, we are at the service. We're bonding at the service. So threaded couplings, guys, is another alternative. A hub is a third alternative. So you have a threaded couplings or bosses made up wrench tied. So the whole idea is to make sure the conduit is really tight as it tied to the equipment. You need to bond them. So here's another alternative for that wire that's called supply side bonding jumper. The hub, we all know the hub. It's, you know, if you have 100 amp or 200 amp service coming from the top, your service conduit is rigid, tied to the service to the meter socket, bonded to the meter socket through the hub. Also, threadless couplings and connectors made up tight for rigid metal conduit, intermediate metal conduit, and electrical magnetic tubing. So these threadless couplings, guys, they have to be rated for bonding. So they have to have teeth. As you tighten them, they kind of eat into the box. So I thought these are a couple of alternatives. Here's an alternative. These are, where's your main bond, where's your supply side bonding jumper? The hub itself is your supply side bonding jumper. Does that make sense? Does that make sense, the supply side bonding jumper? So really the supply side bonding jumper make a big difference, guys, when you're paralleling conductors, really a big difference. Coming to the bottom of a switch gear, a big difference. So I thought, so this is your supply side bonding jumper. You're bonding the conduit into the box. Conduit into the box. So that's the only way. This is your bonding bushing here. This conductor right now here is your supply side bonding conductor. Your supply side bonding conductor. So if you're in doubt and you have a bonding bushing like this and you bond the conduit, you solve almost for all the situation bonding the conduit at the service or anywhere else. All the other alternatives, guys, is there to give you a cheaper alternative for having a bonding bushing really. There's also clamps that a lot of people use, external clamps, and I'm sure a lot of you guys, you have EMP conduits coming to to a box, 3 of them were paralleling. You take a clamp, 1, 2, 3, you daisy chain them and take them to the grounding bar. So bonding bushings. So that's what I thought, especially the material. I'm sure you guys have encountered them and you see them all the time. Any comments, any questions? So that's what I'm going to disregard here. I'm going to go back, minimize that, and go. So that's the whole main reason that number 4 is called the main bonding, supply side bonding jumper. Any question, guys, about the supply side bonding jumper? Supply side bonding jumper. Okay, so I'm going to take the easiest branch. So that's basically bonding and grounding at the surface. Bonding and grounding at the surface. The first thing that you need to do to bring a grounded conductor from the transformer. The second thing you need to do is the main bonding jumper. Bond the neutral to the ground all the way to the grounding electrode system. The third thing that you need to do is grounding electrode conductor to the grounding electrode systems. And the fourth thing that you need to do is the supply side bonding jumper if your conduits are flexible metallic, anything metallic. If your conduits are metallic conduits. So any comments, guys, about bonding? Any corrections? You guys are bonding all the time. Anybody has any suggestion, corrections? Any? Does it make sense? Yes, no? With the pictures and all this good stuff. Okay, now we've finished at the service. We brought our rigid and we bonded the conduits. We bonded the neutral. We sized the neutral. We sized the main bonding jumper, supply side bonding jumper, and the grounded conductor and the grounding electrode conductor. That's number 1 through 4. Now let's go take, that's a couple of chapters in the book, that little thing. They talk a lot of other details, guys, too. It's not like this. And I'm going to leave the transformer for a second. I'm going to go to the easiest bonding after you leave the service. Now, I left my 100 amp panel inside my basement, and I took to a separate garage, an attached garage, not detached, an attached garage, a 100 amp panel. Okay, I have 200 amp in the basement, 100 amp in the garage, attached garage. That's what we're talking about here. Or I took a 2000 amp feeder to another sub panel in the same building. Really, it's the same method. So let's go to this one. This one happened to be, we call it panel board or same building, 1000 amp 48277. Would it make a difference if it was 281 120 or 240 120 single phase? No difference in terms of the calculation. The numbers will be different when you calculate, but the method is the same. Okay, so when you go to the, I want to remind you, we took a feeder from the main panel, the service panel, into another section in the same building, and we need to ground and bond that panel. Cool? Now, as you move out, the first thing you need to do, the code says, is you have to provide 1.2. 1.2, guys, is the neutral for the second panel. So I need to go size the neutral for my second panel, right? I need another panel. I need to size a neutral for it. If I need a neutral, sometimes you might not need a neutral in the second panel. Okay, and then so we'll talk about this one in a second. Then number 6, can you guys see number 6 here? Number 6, this is so-called equipment grounding conductor. Very important, the terminology that you guys are familiar with. It's called equipment grounding conductor. So we ground with an equipment grounding conductor. Number 7 is also very important. Number 7 is called equipment bonding jumper load side. Equipment bonding jumper load side. As you come to the bottom of the switch gear, now you're coming to a sub panel, switch gear sub panel. You're coming to the bottom of the switch gear with rigid or EMP conduit. We need to bond the conduit, like we did in service, to that switch gear. At the service, we call them supply side bonding jumper. At the second building, we call them equipment bonding jumper load side, because they're on the load side of the disconnect is here, and they're on the load side of the disconnect, not in the line side. And who cares that the code treats them differently and size them differently? That's really what cares. Anybody knows why the code cares? Why do they separate them? Anything on the line side of the disconnect, we're doing the overcome protection device, guys, later in this afternoon. If my overcome protection device is right here, anything on the line side here have a minimum overcurrent protection, minimum short circuit and overcome protection device on the line side. On the load side, you should have if you design it well, you should have a proper overcome protection device on the load side, because you have the main circuit breaker to protect you from arc flash and short circuit and everything else. And if you're downstream, you have also the feeder overcome protection device to protect you. That's why the code treat them slightly different. And that's if you go to the equipment bonding jumper load side, always smaller than the supply side bonding jumper. Always. Doesn't have to be that big, because it's not going to handle a lot of current for a longer period of time, because the circuit breaker will trip fast. While here, guys, if you have a short circuit in that conduit here, look at this. If I have a short circuit in that conduit, the short circuit is going to go right through that number 4 into my grounding electrode system, or see in the panel, and it's going to go right through the conduit back to the source, back to the source of the short circuit. So either way, where's my overcome protection device in this area? None. There's no overcome protection device. I'll show you when we do arc flash. I'll show a couple of arc flash later on in the afternoon. If you are to work on the meter socket right here, you cannot have enough PPE or enough size PPE to work on the energize. You have to de-energize the transformer on it, because there's no overcome protection device on the secondary side of a transformer. Typically, the only thing that protects you is the fuses on the primary side of the transformer. And even if cell puts fuses right here, these will be way oversized so they don't trip. As far as they're concerned, your building will be on fire before these wake up. They will wake up eventually and protect the grid, not your building. So anyway, so that's how why the code treat them slightly different. So if you guys don't mind, let's go to 1.2 and size and neutral. Remind you, this is 1,000 amp sub panel. So 1.2, and I call it 1 because it's a neutral. So 1.2, here's my 1.2. Okay, grounded conductor at the neutral. This is at the panel board. Here's how. There's so many ways of doing it, guys. Because I don't have a main bonding jumper here, do I? At the sub panel, I don't have a main bonding jumper. So the size really is strictly based on the unbalanced load, based on the power system unbalanced load, not smaller than 1 aught, because you can't if you parallel, not smaller than 1 aught if you parallel. And here's your requirement here in the NEC code book. So unless you go and get rid of everything 3-phase and size it based on that size, I typically, when I have a sub panel, this is my method. When I size a sub panel downstream, I take advantage of 220.61b, guys. So you take the 2,000 amp size of your panel. The first 200, leave them alone. That's from 220.61. Anything higher than that, the code allows you to chop them by 0.7. Remind you, If you have the unbalanced load, it might give you, and it will give you much smaller size than this. So that'll give you 1460 divided by 5, because I decided to the feeders, I want to parallel 5 sets, give you 292, and when you go to 310.15b16, it'll get you 5 sets of 350 kcm. So that's how you size in neutral at the second panel. Could I have pulled full neutral? Yes. Is it waste of money to pull full neutral? Absolutely. On a panel 2000 amp? Absolutely. What's on the neutral? Not a whole lot. Any comments, guys? Any questions? Any comments? Any questions? So you can again, if you go based on the system unbalanced, you can come up with a much smaller size even than this. Much smaller size. Much smaller size. So that's my neutral at the sub panel. I'm going to go, so that's number 1.2, right? 1.2. I'm going to go directly to number 6, guys. Number 6, if you can go all the way down to number 6. So that will be, number 6 is called equipment grounding conductor. Equipment grounding conductor. That's what the code calls number 6, equipment grounding conductor. How do you size it? You size it based on the overcome protection device, the fuse or the circuit breaker. If you parallel, the code also says if you parallel, you have to run one with every set. One with every set. So you have, I paralleled 5, the old PVC conduit. I need an equipment grounding conductor in each one of them. Each one of them will have the full size of the equipment grounding conductor. So, so if you come over here, the code says 250.122. 250.122 table is get you the size based on overcome protection device. So you take the 2000 amp panel, guys. The 2000 amp, take them to 250.122. That will get you 250 kcm. So your equipment grounding conductor is going to be 250 kcm. I will remind you, the equipment grounding conductor, you do not need to have an equipment grounding conductor. You could have the EMT conduit as your equipment grounding conductor. Your rigid, anything metallic approved by the code, rigid, intermediate, EMT, busway, bus duct, what else? Approved equipment grounding conductor. So these conduit methods will eliminate the need for this type of conductor. A lot of us, guys, if you are using a feeder, we like to pull an equipment grounding conductor anyway with it. Any comments about the 250 kcm equipment grounding conductor? So that's the first calculation, guys, here is for the 2000 amp. The second 2 calculations, I'll go over them for a different panel. So what we did, so 250, and I'm sure you guys are very familiar with the code, and let's just go very quick here into 250 here. 250. Okay, so that's where we were doing all this calculation and looking at all this good stuff. I'm going to highlight one little thing here. Sorry, when you 250.122. Okay, so here's my the table that we were just looking at. I'm sure you guys have used it before. When we said 600, and we came up with 1/0 for the. So you use this table. This table you can use it for grounding electrode conductor, supply side bonding jumper, and main bonding jumper. Main bonding jumper, supply side bonding jumper, and grounding electrode conductor. Use this table. FYI, I believe in 2014 they're going to separate this table. They're going to make one for the grounding electrode conductor and one for all the other bonding jumpers. So it'll be 2. This will be split into 2 tables. They're going to remove the bonding from the grounding. This table. It's going to stay the same size though. So that's the table that we did at the service. I'm going to go directly into that one here, 220. Take a second here, going through the code. There you go. Now, where would you use this table? If you guys have not, especially the ones who have not want to sit for the masters, if you have not used this table, this is you use it for a few locations. Number one, if you're sizing the equipment grounding conductor, that's your baby. And if you're sizing the equipment bonding jumper on the load side, that's also your baby. So two things you can get out of this table. You can get equipment bonding jumper as well as a equipment bonding jumper on the load side, as well as the grounding electrode conductor. So that's and you can see when we got the 2000 amp, my 2000 amp, I came up with 250. And by the way, all the numbers that you have is based on copper. You can find the aluminum easily for these. Okay, so what we did, guys, is let me go back into my sub panel, and then here's my sub panel. Excuse me. So we size the neutral, and we size the equipment ground conductor number 6. Now number 7, excuse me. Like I said, number 7 is bonding your conduit to the bottom of your switchgear. Lock nuts, bonding bushing will take care of that for you. A hub, like we said, like we saw that the service will also take care of you. It doesn't have to be a wire. That number 7, guys, does not have to be a wire. If the conduit match the hole right there too, you can use the lock nuts on both sides tight that get you the connection for the conduits. So the best scenario, obviously, is we have a bonding bushing to attach to the pipe with a wire, and you attach it to the grounding bar inside your switchgear. That's typically you do it if you have a open bottom switchgear. If you have smaller panels, guys, there's a bunch of alternatives, like I said, for that method, exactly like at the service. Okay, number 7. How do you size it though? You size it, if you guys jump, please go to number 7, and if you go all the way to number 7. Number 7, very simple. It says, how do you size? What's the name of it? It's called equipment bonding jumper load side. Equipment bonding jumper, not just equipment bonding jumper, load side. On the load side of the overcome protection device. How do you size it? Same as equipment grounding conductor. You don't have to do anything. Whatever the equipment ground conductor going to that switch gear, you're going to size that equipment bonding jumper based on that one. In my example, the 2000 amp panel board is going to be 250 kcm. So you take a 250 kcm bonding bushings. Now what happened is I have 5 conduits. Do I have to bond? Remember, 5 conduits I have. So can I daisy chain them with the 250, or can I go from each one of them to the conduit with the 250? Either way, if you daisy chain them, guys, if you take conduit 1 to 2 to 3 to 4 to 5 and tie it to the ground bar, that will be 250. Or if you go from one conduit to the ground bar, this also will be 250. Unlike the side bonding jumper, where there are 2 sizes, here the same size. Because we size based on the overcome protection device, not the conduits inside the pipe. Not the conductors inside the pipe. Does that make sense? This is probably the difference between a side bonding jumper and equipment bonding jumper. If you daisy chain or if you go home run from each one of them, the size is the same. Side bonding jumper will be different, completely different sizes. Here, the equipment bonding jumper is sized based on the overcome protection device. The overcome protection device. Any comments, guys? Any questions about that?
Why would they do that? It doesn't make sense.
Well, because we already oversized the equipment bonding jumper on the load side. We sized it based on the 2000 amp, not on 1/5 of the 2000 amp, right? So it's already oversized to cover the worst scenario, which is the 5000 amp. Now, if you go from each conduit, this is done. Here's to make it easy to understand. Okay, you have 5 sets. Do you have to form the same equipment ground conductor with every set? Yes. Because the code says, what if you have a short circuit in one conduit? ground fault. Say you have a ground fault in one conduit, then all the ground fault is going to go directly through that conductor. All of them. It's not going to split between the other two or the other three. So they wanted to be able to handle the full ground fault current that could go through it if there's a ground fault in one conduit. This is the same thing. If there's a ground fault in one conduit, that equivalent to grounding conductor, you don't want it to arc. Any comments, guys, about the equipment bonding jumper? Anybody knows why we bond the conduit to start with? Who cares? I already have an equipment ground conductor. Why do I bond the conduit? If you guys have, if you have a ground fault, if you have a ground fault in your system, and you have an equipment ground conductor and a metallic conduit, the current would have two paths. One path for the ground fault is going to go through the equipment ground conductor back to the source. The other path will be through the conduit. And the current is going to take the least resistance path. And there are studies, if you read through that book, it says if you have an EMP conduit, especially metallic conduits, actually the majority of the current will go back, surprise, not on the equipment ground conductor. It will go back on the shell of the conduit. So if these are not tight, they will arc and burn. But that's your least problem is arcing problem there. It will not allow the overcapacity device to trip fast enough before it starts the fire. So that's why we care about tightening them. Yes, we're not using him solely for equipment grounding conductor, but the current doesn't care. It sees a path, and we jump into that path and go back to the source when it has a ground fault. Any comments, guys, about the equipment ground conductor and the grounding electrode conductor, and equipment grounding conductor and the main the equipment bonding jumper load side? So that's it. If you have a service inside your garage, that's what you're attached building. That's basically how you're going to handle it. You're going to have an equipment grounding conductor and an equipment bonding jumper load side, and you have to bring the neutral and size your neutral. I'm not talking about the phases. Of course, how do you size the phases? Based on the panel. If this is a 2000 amp panel, you load it to 2000 amp and you find the feeders for it. Any comments, guys, about this sub panel? Before I go, I'm going to go to another sub panel in different building now. And the reason why different building, because there's grounding and bonding requirement. So let's go a little bit down, guys, here, right in here. I'm going to focus on another switchgear or panel board in a separate building. So I took a 2000 amp, another 2000 amp out of this switchgear to a separate building, physically separated from each other, or structure, and I have another panel there, and I need to feed it. When you feed a separate building, guys, the code says the following. Number one, as your feeders enter the building, you're supposed to provide, as my feeders enter the building, you're supposed to provide an overcompression, a disconnect right here. So here's my building. You enter the building, you have to provide a building disconnect or a structure disconnect. That could be your circuit breaker or a fuse disconnect. Right? Everybody knows that one, right? So that's number one, but we're not talking about the disconnect now here. We're talking about the grounding. As you enter the second building, you're supposed to establish a new grounding electrode system as if it was a service. Exactly like if it was a service. As if it was a service, meaning you have to have at least one grounding electrode system, at least, but if there are other grounding electrode systems in the building, you have to tie to them. So what you end up doing in the second building is, say it's a bigger building, and the same thing, you have a ground. This is a bigger building, so I have a ground bar, and I tie to all my grounding electrode system here. You need at least one. But if the others exist, you have to add to them. And keep in mind, guys, that also the code says if you're only one grounding electrode system is a ground rod, you need to supplement it. So you end up with two if you have a ground rod or a pipe or water. You have to supplement it. That's the only. But if you have steel in the building, You can only need the steel. But if there's water coming to the building, you have to tie for the water too. So that will be a steel, the frame of the building, as well as the water. That will be the tool that you need. Do you want to drive another ground rod? It's up to you. So, at least you need one. So here's what they do. So then you have a ground bar, and then we have 3.2, which is this is grounding electrode conductor. This is also called at the second building grounding electrode conductor. And we need also number 6. You guys remember number 6 is also an equipment grounding conductor going to second building. And we need number 7, which is also bonding the conduit if it was metallic conduit. If we're coming with a conduit, you need to bond the conduit. So the only difference between this sub-panel and the sub-panel right above it, the only difference, guys, is we are creating a new grounding electrode system at the second building. You do not, I want to bring to your attention, you do not bond the neutral and the ground at the second building. You see, completely separate them. There is no main bonding jumper here. Other than having a main bonding jumper, what you're looking at right here, guys, is very similar to a service. Exactly like another service. The only thing we don't do is we don't bond the neutral to the ground. Because that will provide multiple paths for the neutral under normal operating conditions. Hey, my friend, how are you? Good.
Yeah, I just want to let you know I'm going to lock that front door. I'm going to head home and then unlock it remotely so you don't have to use cards or anything. So.
Oh, okay. Okay, thank you. So that's the only thing that we're going to provide. So I'm going to go, guys, quick right here and just show the 1.2, the size of the neutral. I'm going to show the let's go to 1.2 quick here, and these are the ones are the neutral. I like to pick on the neutral. So where's my 1.2? 1.2 grounded conductor. What is it? Okay, we are 1.2 for the same panel, right? Yep, 1.2. So that we size the neutral, guys, based on the rating of the neutral. Is 1.2. I took the 200 amp, leave him alone. Anything higher than 200 amp, cut it by 0.7. You end up with 350 kcm for that neutral. I'm going to go there also to the, so that's my neutral going there. I'm going to also go to number 6, which is the equipment grounding conductor that you have to provide with it. So let's go to number 6 here. So here's my number 6. I have my 200 amp, my 2000 amp, same thing, is going to go 250 kcm. And number 7, guys, it's also going to be 250. So everything is going to be the same. The only difference is you're providing an equipment grounding electrode conductor. So for the separate build, for the other building. So let's go to 3.2, guys, if you don't mind. I'm going to look at that's really the only difference here, 3.2. So if you don't mind going to 3.2 to size the grounding electrode for the second building. So here's my 3.2. Okay, grounding electrode conductor, separate building. You size it. I'm going to summarize like the service, exactly like the service, based on ungrounding conductor. So I have 2,000, 5 sets, get you 400, 600 kcm each. You multiply them by how many sets, and you go to 250 to 66, get you 3 out. Any comments, guys? Any questions about the grounding electrode conductor at the second building? You treat the feeder like a service conductor, and you size the grounding electrode conductor based on the feeder conductors. Any comments? Any questions about that? So that's that's basically what you're going to be doing, and the same minimum. So here's what I said also, guys. I said, based on the feeder conductors, if the feeders are parallel, you have to multiply them by their sets, not larger than 3/0 or 250, minimum of 1 electrode connection. If other electrodes exist, they must be used. So just summarize the whole requirement. And if you don't believe your friend Chad, or you're going to go check, I have the 250, the 32, and 50, and 52, and so forth. Any comments, guys, about bonding at the second building? bonding and grounding in the second building. So that's your grounding electrode system. The same thing, guys, when you go to the second building, if you have a ground rod, you do not need to go larger than number 6 for a ground rod. High, no larger than number 6. Ground drain, they say number 2. The whole requirement that applies to the service, the minimum, you don't have exactly apply to the second building. For the, do we, yes, sir.
What about the gas line of the second building?
Well, the gas line is not approved as a grounding electrode system. So you're not supposed to tie to the gas line and use it as a grounding electrode system. If it's above ground, you have to bond it. But that particular one is about using it as a grounding electrode system. So, yeah, it's not used as a grounding electrode system. Okay, so that's basically the requirement of the second building. For do we have a power limited technician guys too, right? For the power limited technician guys, the code says, guys, you're required to provide an inter-system bonding device or equipment. It looks exactly like this bar, right by the service or this connector or the meter. For the low voltage guys to go and tie their own so-called, now they change them. It used to say grounding conductor. Now it's grounding electrode conductor or bonding conductor. So you have to have an inter-system bonding terminal so you can tie the low voltage stuff into the system. This is required at the service. So that if it's a bigger building, guys, that will act right here. That system at the top here can be your inter-system bonding terminal right here, where the low voltage guys can also tie their system, or they can take a number 6 conductor, put another bar somewhere else and tie to it. What I want to emphasize is when you go to the second building, the code also requires you to provide the same thing at the second building, exactly the service. So as I go to the second building, if you read, so now I went to the second building, I'm supposed to provide an inter-system bonding terminal for the low voltage systems to be tied to. In my case, that grounding bar will act as inter-system bonding terminal. But if I'm not using a ground bar, I'm supposed to take number 6 to a set of logs by the service as you enter the building. So the low voltage satellite dishes and coaxial cables and so forth will be tied to it. I can't emphasize that enough. So the second building is treated as a service in terms of an inter-system bonding terminal. Any comments, guys? Any questions about bonding at the second building? Bonding at the second building. So you end up, when you guys have a 3-phase system, you end up with the 5 conductors inside your PVC conduit. You have 3-phase and a neutral and an equipment grounding conductor. If you have a cable, you're feeding with cable, 5-conductor cable, including the equipment ground conductor. There's exceptions when you go to the second building, guys, where they allow you to have 4 conductors in a 3-phase system, and you bond the neutral to the ground only for existing buildings, only where there is nothing metallic between building A and building B, and nothing exists, no metallic object tie building A to building B. So I always don't even mention it. The rule is 5 conductors in a PVC conduit if you're going underground, or if you're having a cable, it's going to be 5 conductors in 1 cable, counting the equipment grounding conductor. Does that make sense, guys? If you're using single phase, right, so you're dropping 1 conductor, so you're looking at 4 conductors, right? 2 hots and a neutral plus the equipment ground conductor.
But you can run 3 conductors if you don't have anything metallic between.
For existing, yes, for existing buildings though.
Oh, for existing buildings.
Yes. So you can't go build a barn or go build another building, another shed, and treat it this way.
But you can have an old building sitting there and then you can run 3 conductors to it?
It will be very hard to pass the inspector. You pull because you're trenching, and you're going to put a cable. You put the 5-conductor cable. So really, that exception is not meant to almost to be used even. So the only thing I can think of is the farms. On the farms, they use a lot of that one. But yeah, so anything new, if you pull your conductor, it's going to be you have an equivalent conductor with it. Anybody have an inspector that allow you to pull a conductor to a separate load outside without an equivalent conductor on that? I can't think of any location. Do you? You guys? Existing. And you pull the cable? No? Yeah, existing cable. Yeah, existing cable to use, yes. Yeah. So it's really the exception. The rule is you pull an equivalent ground conductor and you isolate the neutral from the ground. And the idea, guys, because if you tie them together under normal operating condition, your water, if there's a water pipe between the two buildings, the water starts getting hot because the current is going. What's better than a copper pipe, if it's copper, taking to carry the current back to the source? It's much better than your number 1/0 conductor, right? So the neutral will jump into the copper water pipe and goes back to the source. Who cares? You start getting hot water when you're not supposed to, and it could be also a hazard. Of course, it is a hazard, shock hazard and arc flash hazard and so forth. Any comments, guys, about this one? Any comments? So that's really not a whole lot on that one. I'm going to go. Do you guys have energy for going to talk about transformers now? Separated drive system. Now we finished at least 4 chapters based on what we did now. Separated drive systems. So really the grounding and bonding, guys, every one of these has its own unique characteristics. So we ground and bond at the service. You saw how we did that. Or ground and bond at a sub-panel in the same building and another sub-panel in a different building. Now we're going to do 2 unique things, which is separated drive system. A separated drive system, guys, is a unique name when 99% of the time, you're creating a new neutral. You're creating a new neutral, and you're isolating your new neutral from the old neutral, if any, inside your building. That's I always explaining it without getting into all the details. Is what's a separated drive system? You create a new neutral, take a transformer, delta Y. On the secondary side, what did you create? A neutral, right? So now you have that's called separated drive system. And you isolate the neutral on the secondary side of the transformer from the neutral on the primary side of the transformer. Do you tie the neutral of 277 with the neutral 120? You're not supposed to tie them together. If you have a generator, you create the same thing. You're creating a neutral because you're creating phases anyway. Now, the only thing that it becomes, is this a generator separated drive system or not? It's one question. Are you isolating the neutral of the generator from the neutral of the building? Yes, separated drive system. No, it's not a separated drive system. So I always say the key word to remember separated drive system is you create and isolate the neutral. If you do that, you have a separated drive system. Does that make sense? In plain English, without getting into all the details, you create and isolate a neutral, you have a separated drive system. Now, who cares? When you have a separated drive system, guys, and when you isolate your neutral, now I have a new neutral that's isolated from the old neutral. I need to do a few things for it. First thing, I need to bond it. Because when you have a neutral that's not bonded, guys, to the ground, if you lose it, you have a floating neutral. What happened with having a floating neutral? Floating neutral, you have 208 shared between a bunch of fixtures that rated for 120. So they're going to start dimming and going up and down, and you burn the ballast on them, or you burn certain equipment, right? Because they're not rated for 200 volt, they're rated for 120. So like opening, if anybody multi-wire branch circuit, open a neutral multi-wire branch circuit and see what happened, right? You burn a few things if you haven't done that yet. So that's the reason why it's important to go to a separated drive system, and really, you created a neutral, now you need to bond it. Okay. So here's my second example, guys. I brought a feeder from the switchgear through a conduit, and I like metallic because there's bonding to it. Then I went to the transformer box. You have to have a transformer. It's typically delta Y. It doesn't have to be, but typically delta Y, because I don't need a neutral on the primary. I created my neutral, that white. I call it white because that's typically the color that we use on the 28120. And I created a 28120 system, and I dumped that system across a panel that's called 28120 panel, right? Typical. You guys do that all the time. So here's my example for you. So that's what we have. The example that I have, guys, is I have a 750 kVA 480 28120 transformer, primary 480, secondary 28120, and it's dumping the power at 225 amp panel 28120, all three phase, right? And your job and mine is going to be to size the following. Number one, the newly created and bonded neutral. Can you guys see I created that white neutral here, right? And I bonded it. Can you guys see number 5 here? That's the first thing you do. You bond the neutral. That's number 5. That's now this is, instead of calling it main bonding jumper, it acts exactly like a main bonding jumper. They have a fancy name for it. They drop the main and they add system. They call it system bonding jumper, but really the concept is the same. The way we size it is also the same. Instead of just to distinguish it from the main bonding jumper at the service, they call it system bonding jumper. Why system? Because we created a new system. Does that make sense? So that number 5 is called now system bonding jumper. 1.2, that's also called grounded conductor, aka neutral, because I created new neutral, right? That's 1.1, my neutral. Then you get into number 4.1, guys. Oops. You get into 4.1. 4.1, that's what I want to emphasize a little bit. This is also called supply side bonding jumper. Supply side bonding jumper. That's bonding the panel enclosure into that transformer enclosure. You can do that one through, you have to bond the conduit through a wire going between them, or you can have conduits and you have to bond the conduits from both sides, typically through a wire, because we use a flex in between them. So let's just go, if you guys don't mind, so everybody understand what we're doing. We have 225 amp panel, 28120, fit from a transformer 75 kVA, that's fit from a 4000 amp switchgear, right? So let's start with 1.1 and go size 1.1. I want to remind you the panel is 225 amp, so size the neutral for 225 amp panel. So 1.1, here's what I do. I called it secondary ungrounded conductors. So I take the 225 amp panel first and size the phase conductor. 4-aught, right? You get 4-aught for this panel. Then, so this is your 4-aught. For the neutral conductor, guys, so then what to size it, here's what it says. Based on the power system unbalanced load, the neutral, and not smaller than the supply side bonding jumper. So remember that, say not smaller than the main bonding jumper, not smaller than the supply side bonding jumper. Same thing. So that neutral cannot be smaller than the supply side bonding jumper. So I size the phases here, 4-aught. My supply side bonding jumper, you take the 4-aught to 250.66, give you number 2. So really my neutral shall not be less than number 2, right? The minimum neutral you can do is number 2. What now because the supply side bonding jumper is number 2. The reason why I put 4-aught, guys, because these are receptacle panels, and a 225 amp panel, it's a tons of neutral load. So personally, that's opinion. That's an opinion, not a code. I like to pull full neutral up to 225 amp panel. That's what I highlighted here is an opinion. 4-aught neutral is an opinion. The minimum that you need is 2-aught. Do you guys pull full neutral for these panels at 225? It's a low, everything in the panel is neutral, right? When you have a receptacle panel, almost 99% of what you feed there is line to neutral, right? Face to neutral, face to neutral. So anyway, so what's your minimum? Number 2, what I highlighted here is recommendation full neutral at this lower level, just because everything, the load, guys, there is neutral load. And there's also harmonics now, because equipments and so forth. From a safety point of view, full neutral would be the best. At this level, we're at 225 amp panel level. Could I use number 2? Absolutely. Okay. Any question, guys, about the grounded conductor? How we came up with the size of the grounded conductor? Not smaller than the system bonding jumper. What's my reference? Here's your reference, guys, right here, without getting into it. Okay, so I sized my neutral. My neutral came up with the minimum number 2, but I decided to use full neutral, so-called full neutral, number 4-aught. Then I'm going to go size, so I size my neutral. I'm going to go size number 5, guys, is the main bonding, not main. This is the system bonding jumper. The system bonding jumper, we say, we just size it. Let's just go directly to number 5. Okay, the system bonding jumper for a separate drive system, please just pay attention to the transformer. XFR, the transformer, ungrounded conductor 225, 4-aught. The system bonding jumper, you take the 4-aught to 250.66, get you number 2. To size the system bonding jumper, here's what you need to do, guys. You size it based on the separate drive system feeders. If you parallel, then you have to multiply by their sets, and you cannot, if you are more than 1100 kcm or 1750, you have to use the 12.5%. So long story short, it's the same rules like the main bonding jumper. Same rules like the main bonding jumper, except to use the feeder to size them. Any comments, guys? Any questions about that? Any comments? Any questions about this one? So that's my my system bonding jumper, my so-called system bonding jumper. You drop the word system and you say man. Exactly, the way we treat it, exactly same. So the last thing, guys, in this system, if you go back, now I have a flex. Now I have my transformer. You grab your transformer. Oops, there you go. There's mine. So you grab your high voltage panel, guys, here, and you came set to your transformer. And here's my, this is my 480. This is my 208 system here. This is my XFR. Now, here's my overcome protection device sitting here. Let's just say from the bottom, fed bottom. And now you need to bond the two enclosures together inside the conduit or outside, right? Because we typically use a flex. That wire here is called the supply side bonding jumper. Does it sound familiar? That's exactly what we use at the service to bond the conduits. Supply side bonding jumper. So you bond this enclosure to this enclosure through a wire that's called supply side bonding jumper. Why supply side? Because it's on the supply side of a disconnect of the separately derived system. So because the disconnect of a separately derived system is right here, right inside the panel, and we're bonding this enclosure to this enclosure because we flex them. We don't want to depend on the flex to do the bonding for us. So we're gonna take our wire. So if you go there, when you size it, guys, 4.1. If you look at 4.1, the way we size it, here's my 4.1. Very simple. It's the same as supply side bonding jumper. Same size as supply side bonding jumper.
So let's say you use flex. When would you need to have a supply side bonding jumper? If you go conduit and have, let's say you're using flex.
You have to pull a wire in between.
Just pull a wire.
Yes. Yeah. So what you do when you use a flex is you pull a wire, and it will be right here. You put your fitting right here, so the wire is coming in here. You tie your conduit on this side, and you continue. And another fitting right here. You tie your conduit on this side, and you continue to this. So it's one wire. You pick the conduit from both sides, and you tie it to the other. So you bonded the conduits, and at the same time bonded the two enclosures. See what I mean?
So if you run EMT between the transformer and the thing,
Do you want to run EMT to vibration and so forth?
just
Yeah.
hypothetically.
Yeah. If you run an EMT conduit, then you go into the methods of bonding at the surface. The conduit match the hole, tight lock nuts on both ends, or a wedge, or bonding bushing, and you do not need a wire. Long story short, the wire is disappear. Yeah, but then you have to have bonded both ends though. But the only way, typically for smaller ones like this, unless it's a big transformer coming from the bottom with a conduit, and if that's a bigger transformer, you're coming from the bottom here, like here, then these will be PVC anyway, so you don't have to worry about these, right? And then you just pull a conductor inside the PVC to bond the two equipments together. Any comments, guys? Any questions about that? So that's your bonding at the separated drive system transformer. Separated drive system transformer. So we size, guys, the main bonding jumper or the system bonding jumper right here. We size a neutral. We size the supply side bonding jumper. And that wire that I'm showing right now here, guys, it really could be one wire. Just tie the end of that, the connector here, and tie the connector here, and then bring them all both as one piece of wire. The last thing I'm going to mention, guys, is now what do we do on the primary side of a transformer? So that's the secondary side of a transformer, right? So we know this is separated drive system. I created neutral, and I have my system bonding jumper and so forth, everything here. So how about the primary side of a transformer? Don't you need an equivalent ground conductor to go to right here, this side? So we covered this side here. How about this side from here? As far as this panel concerned, this is a load, and it needs an equivalent ground conductor, right? So now looking at it, the high voltage side of a transformer. So you need, with the high voltage side of a transformer, you need same thing, guys. Can you guys see that wire here coming here? That could be the same wire. Tie the flex in both sides, here and here. Go through it. Tie this piece of equipment to this piece of equipment. Exactly the same thing that this piece of wire do, except it's sized differently. On this side, they call it supply side bonding jumper. On this side, when it does the same thing, this is called equipment bonding jumper load side. On this side, it's called equipment bonding jumper load side because there's an overcomputation device ahead of it, and that guy is going to take care of the ground faults if you have any ground faults here. This piece does not have an overcomputation device after the transformer, right? There is nothing. On the secondary side, you have to go through the primary to find it. So they treat them. This is supply side bonding jumper. This is equipment bonding jumper, load side, or it acting, and also equipment grounding conductor. Also equipment grounding conductor. If you tie it the way I said, you tied it on both sides. The same wire acts as your equipment grounding conductor, and your equipment ground conductor, and your equipment bonding jumper on the load side, because it bonded the conduits, the flex, on both sides. Any comments, guys, about that one? So going to this side, this is where number 7 is. Can you guys see that number? I have it here. I have it here as number 7, and number 7 here. That's the equipment bonding jumper load side, and number 6 is the equipment ground conductor. It could be one wire, does both functions. It can't be a conduit though, because you don't want to conduit directly to the unless you come, like I said, come from the bottom. So it could be one wire. 7 and 6 here could be one wire. So if you guys go all the way to 6, let's go to 6 here and see what we have, how we size it. Number 6 for the transformer. Look at that. Here's at the bottom. I did for the transformer 750 kVA divided by the voltage and the 3-phase multiplier. Get you full load amp of this size at 125 because there is no secondary protection. Get you 150. So 125 amp. I size. The first thing you need to do is size this guy as 125 amp fuse or circuit breaker, right? Typically, and then. From 125 amp, go to 250.122, and that will get you, gentlemen, number 6 as your minimum, number 6. If you look at, that's the equipment ground conductor for the transformer. If you look at the equipment bonding jumper, the same thing for the transformer, guys, right here, with the last bullet, it's also number 6. These could be one wire or 2 separate wires. Typically one wire, you lube the 2 sides on the lug nuts and you continue with them. Any comments, guys? Any questions about grounding and bonding on the primary side of a transformer for the separate derived system, as also grounding and bonding on the secondary side of a transformer for a separate derived system? Any comments? Any questions, guys? Now here's a devil advocate. And what happens if you have a delta-delta? Anybody have seen a delta-delta transformer? Isolation transformer. First of all, is this a separate derived system? Based on the code definition. Now I have a delta-Y. I created and isolated the neutral. That's how I define it for you. How about if you have a delta-delta? If you guys read through the definition of a separate derived system, it says complete separation between all the conductors of one system from the other. I focused on the neutral because the neutral could be tied, but can you tie the hots of this and the hots of this together? You get yourself a short circuit, right? You cannot tie them. So as long as these are completely isolated from each other right here, which they should, the only time they can't be if it's an auto transformer, right? An auto transformer, if they're separated like this, then this is separate derived system, and then you have to treat it exactly the same way. This will be treated the same bonding, exactly the same separate derived system, same way we did it. Nothing will change. The only thing that the only thing that would change is the main. Remember the neutral and the ground here. There's a neutral and there's ground. The 2 bars. There is no neutral now. So I have to tie to my ground, and I have to establish my grounding electrode system here. We didn't talk about this one yet. But there is no neutral bar, so you just don't bond the neutral to the ground because there is no neutral. This is also a delta-delta, a separate derived system. Does that make sense, guys? If you have a delta-delta system, it is a separate derived system. Okay, so that's my, the last thing I wanted to talk about in this transformer, guys, before I give you a quick break here, is right at the transformer, the code require you to tie to the grounding electrode system of your building. So I don't know if you guys can see that wire, number 3.1. Can you guys see that one? 3.1 going all the way to the grounding electrode system inside my building. If you have a separated derived system, typically you already established the grounding electrode system in the electrical room, right? It's already there. So what you do is you take a conductor, insulated, bare, or covered conductor, grounding electrode conductor, and you take it all the way to the grounding electrode system that you already established. That's one method. Method 2, if your building is steel, complete bonded steel together, and your transformer is one end of the building and your service is at the other end of the building, you do not need to go all the way to the other end of the building. You can directly tie to the steel on the east side. Where's the east side, and the west side where the service is. You don't have to take ground electrode conductor all the way to the service because they're all bonded through that steel building. If it's not a steel building and it's not bonded together with a ground ring and all this good stuff, then you have to take a grounding electrode conductor all the way to the service and bond it directly with your grounding electrode system at the service. You also have to drive a grounding, create a grounding electrode. Only if this transformer is outdoor. So if that transformer was outdoor, separate derived system outdoor, not indoor, then you have to drive a ground rod right where the transformer is located. That's it. And you still have to and bond it right at the transformer, and then the equivalent grounding conductor that you brought will bond the two together. The equivalent grounding conductor that you brought will bond the two grounding electrode systems together. That's if you are outdoor. If you're indoor, all what you have to do is take that wire that I'm pulling right here all the way to the closest grounding electrode system in your building that's bonded to the rest of the grounding electrode systems. Any comments, guys? Any questions? Any comments? Any questions about that? So if you look at 3.1, how we size 3.1, 3.1, here's my transformer. If you look at the transformer, for transformer, you have to find the full load current for it. I mean, you have to size the feeders for it. And for based on 4-aught 250.66, you get your number 2. So I need a number 2. I need a number 2. Any comments, guys? Any questions? Any comments? Any questions about that? Any corrections? If you find something that doesn't make sense, please let me know, guys, too. Any comments? So that's basically the magic of grounding at a separate derived system. If the transformer part of it, just the transformer part of it. So you can see coming from one to another. And I like the numbering, guys, because hopefully it will help you kind of tie into the way we do the calculation. So when we have a separate derived system, guys, you bond the neutral to the ground. You have to pull a new grounding electrode system to be tied to the grounding electrode systems in your building. You have to have something called supply side bonding jumper that tie on the secondary side the two equipments together. On the primary side, you have to have an equivalent grounding conductor and or main equivalent bonding jumper load side. It could be the same wire to tie the two equipments together, and they're sized differently. Any comments? Any questions? Should we have 5 minutes? Okay. Okay. Any comments, guys? Any questions? Any corrections? I think we created a lot of discussions on for the grounding and bonding. The last thing I want to talk about, guys, before I start flashing a couple of pictures with you, let me turn my email off here for a second. So that must be your email. The last thing I want to do, guys, so just a quick summary. We did grounding and bonding at the service. We did grounding and bonding at the separate derived system via a transformer, and we did grounding and bonding at 2 different panels. The only difference between them is one in a separate building, really. And the last thing I want to do is generators. So let's go up here and have Mr. Generator sitting right here. 1, 2, 3, or how many you have, and ground and bond the generator. I decided single-handedly to run my generator separately derived system. Separately derived system. So I created neutral, and I want to isolate my neutral that I generated from the neutral of the utilities. The only way you can do that one is if you have a 4-pole auto transfer switch or manual transfer switch. That's the only way you can do it in a 3-phase system, right? You can have isolate the 4 conductors that's coming, the 3 phases as in the neutral, okay? And we'll talk about the non-separate derived system. This is separate derived system. Okay, so I have separate derived system. It's 250 kW, guys, 48277. Right, my transformer is inside my building because it makes a difference. If you not transformer, if the generator is outside the building, you have to drive a ground rod right next to the generator, ground it because of lightning and so forth. My generator is inside the building. The first thing you need to do is take a grounding electrode conductor from the grounding bar of the generator all the way to the grounding electrode system of your building. Does that make sense? Like the transformer that's inside the building. I will remind you, inside the building. So here's number 3. Number 3, guys, is the grounding electrode conductor for the generator. You have to provide a grounding electrode conductor for the generator. Okay, so then we have number 5. Number 5 is called, instead of main bonding jumper, it's a separator of system. They call it system bonding jumper, exactly like the transformer. System bonding jumper. And I bonded my neutral to my grounding bar inside the generator. So that's my system bonding jumper. And number 1.1, I call this one, guys, the grounding conductor, the grounded. And the reason why we include it, because it's part of the grounding system, grounding and bonding system. So I have my grounded electrode conductor coming in here. The fourth thing that we have to pay attention is 4.2, guys. This wire here, this is called, it could be called two things. I'm going to call it, I'm going to remind you what my situation could, this could be two things. I'm going to tell you what my situation is for this transformer. My overcome protection device is not sitting right at the transformer. It's sitting inside the switch gear. You could, right? You could put your circuit breaker inside the switch gear. So if your circuit breaker is not right by the transformer, this 4.2 is called supply side bonding jumper. Supply side bonding jumper. If your circuit breaker is sitting right here, as a lot of them are, you have a disconnect circuit breaker sitting right there at the transformer, this number 4 becomes equipment grounding conductor. That's it. So that's now the way the scenario that I'm running right now. I'm putting my circuit breakers inside the switch gear, pulling it and putting it right here. So that's my supply side bonding jumper. So I'm going to go, guys, and just look at sizing it. So we have the system bonding jumper, number 5. We have 3.1, which is the grounding electrode conductor. We have 4.2, which is bonding the conduit and bonding the two equipments together, which is that conductor right here. That's going to bond this piece of the generator into basically the switch gear. The generator, it's going to bond the generator into the switch gear right in here. And then, of course, the neutral. So let's go size the neutral, guys. 1.1. I want to remind you, it's 250 kW, 482.77. So let's go 1.1. Very easy. So here's first you need to size the phases. Here's my, I put them right here, guys. The stuff for the generator, because not enough room. So generator ungrounding conductor. You know how to find the full load current of the generator, guys. Piece of cake, right? And then from there, at this level, guys, at this level, you have to multiply by 1.15. But at this level, typically you go to the next standard overcome protection device because they're adjustable. So that's what I did. So I took this amount of amps, I divide by 0.8 to get me the kVA if you're confused with that one. And I got myself 2000 amp load or circuit breaker. And then I'm going to size my conductor based on that circuit breaker, basically, at that level. So I got myself 5 sets of 600. Then to size a neutral, I applied my rule of, I don't have full neutral for these. So I just applied the rule of 220.61b, guys, to get you less size neutral. 0.7 for anything higher than 200, and came up with 350 kcm. So I'm pulling 3 conductors 600 kcm and 1 conductor 350 with this generator. Cool. Could I pull less than that? Absolutely, especially when the neutral. And the only thing you can justify pulling less than that is you have to find the load on the generator and remove anything that's 3-phase when you calculate the neutral. And remember, we're paralleling it. So whatever you come up with, you can't go less than 1. Why not? So if you can prove that your load is really less than that, you can go with 1 odd. Okay, so that's my neutral. If you guys go to the next one on the generator, my gen, I'm going to go to number 5. Number 5 is the main bond, the system bonding jumper for the gen. So if you guys go to number 5, if you don't mind, and just focus on the gen. Here's number 5. I say generator system bonding jumper. You take the phases, the phase size, which is 600, multiplied by 5, And then same thing, guys, like any system bonding jumper, get your 375 kcm, and you go to chapter 9 table 8, get you 400 kcm. So that my system bonding jumper is 400 kcm, or it could be UL listed copper piece inside, came with the generator that you bonded together right there. But if it's a wire size, that's the size that you need for the main bonding jumper. Any comments, guys? Any questions about, I mean, the system bonding jumper? The system bonding jumper for the generator. So if you, so that's my system bonding jumper for the gen. Then I'm going to go size 3.1, which is the grounding electrode conductor for the gen. Same thing. You're going to take it. So if you guys go all the way to 3.1, focus on the gen. 3.1, here's 3.1. Okay, here's my gen. Same calculation, 5 times 600, give you 3,000. You do not need to go larger than 3/0. Because you do not need, exactly like at the service, you do not need to go larger than 3/0. Any comments, any questions, guys? There are projects that we did as engineers, and we use 500 kcm as grounding electrode conductor. You know, there's a lot of projects that go much higher than that. Hospitals. That's the bare minimum. So obviously, the larger the better. You're talking about when dealing with grounding, guys. You're talking about grounding as well as lightning. When you have a complete holistic grounding electrode system for your building, a lot of people have a ground ring up to 500 kcm around the whole building, tying it to the steel of the building. Have a couple of grounding electrodes on ground rods, tying all together and bringing a 500 into the copper bar, and then start tabbing from 500. That's not uncommon to do for a system like this. But these are the bare minimum that you can size for. Okay, so that's my grounding electrode conductor. So number 5, the last one, guys, and number 4.2, way at the bottom here. Number 5, we got that one for the gen, I believe. Here's my 5 for the gen. We came up with 400. 4.2, though, I want to focus on 4.2. You can see it right here. Supply side bonding jumper, separately derived generator, 400 kcm. Exactly, if it's supply side bonding jumper, guys, it's treated as this is treated as a system bonding jumper. And also for a non-separated derived system, so if it's separately derived system or non-separately derived system, the supply side bonding jumper stays the same. Doesn't matter. The only difference, if it wasn't a separately derived system, so that does not, supply side bonding jumper, regardless of its if it's for generator, regardless if it's separately derived system or none, the only difference, if that one was, they just come over here, the only difference, if this generator was not running separately derived system, the only difference is that number 5 will cease to exist. You just remove that system bonding jumper is not there. Everything else stays the same. All the calculations stays the same for separately or non-separately derived generators. Any comments, guys? Any questions? Any comments? Any questions? Now, this is, like I said, this one assuming that your generator okay, so many technologies. So let me draw here so you can see it. Any comments, guys, about the way that this scenario that we ran? Does it make sense? Is there any corrections? Anything that you guys can see?
Questioning is what is a separately derived and what it's not when it comes to generators.
Okay.
Is it the location of the disconnect?
It's bonding that. Well, it's isolating the neutral. The bottom line. Do you isolate the neutral or not? You isolate the neutral, separately derived system. You don't isolate the neutral, it's a non-separately derived system. How do you isolate the neutral? You can isolate the neutral in 2 ways. In a smaller system, guys, auto transfer switch and manual transfer switch, 4-pole. In a bigger system, you talk about 4-pole circuit breakers. Power circuit breakers, 4-pole. If you are to have a assembly derived system. Typically, they don't have a assembly derived system. So you have a 3-pole circuit breakers, a non-assembly derived system. If you have parallel switchgear, 3-pole circuit breakers, and the neutral is bonded for the whole system. So does it make sense? So that's basically that one. So let me just grab my pen here. Let's get you that color, guys. So here's my generator, Mr. Generator sitting right here. So if I pull my conductors, guys, and I come to my switch gear, here's my switch gear, and I put my circuit breaker inside right in here, and that's my main for this switch gear coming from here, and these are all feeders. Okay, so here's my gen. My gen is sitting here. My gen. So then this wire right in here, coming in with the gen is and tied to inside that's the ground bar. That wire, guys, like we said, it's called supply side bonding jumper. In this case, bonding jumper. That's typically if you have parallel switchgear. That's what you do, because you don't put the circuit breakers right at the generator. You don't want somebody to trap them. So you're paralleling switchgear typically like this. And now, if you have a neutral, here's my neutral. So if you bond the two together here, this is a ground. If you bond the two together, and of course this is also you have to have take this one to the ground too, the ground bar inside your building typically here, the ground bar. So that's how you do a separately derived system. The only thing, and so this is my system bonding jumper right in this area, system bonding jumper. If your system is not separately derived system, guys, the only thing that goes is that connection right here. You just get rid of that connection. Everything stays the same. Now this is scenario 1. Scenario 2 is this one. What happened? Any comments about this, separately or non-separately? The only difference is, do you have a system bonding jumper here, or you don't? Now what happened, guys, if I have a generator and I put my fuse disconnect right in here? So here's my wires coming in here, right? So that's my circuit breaker right here. Now everything stays the same except that wire that goes from here, from the ground through this one into the ground here. That wire, if your disconnect is right at the transformer, now it's called equipment grounding conductor. And how do you size it? You size it exactly based on the equipment ground conductor, based on the overcome protection device. Any comment? Everything stays the same. The neutral same size. Does it matter if it's separately derived system or non-separately derived system? It really doesn't matter. Everything stays the same. The only thing that changes is that wire that we took right in here. Instead of supply side bonding jumper, it's going to be equipment grounding conductor. Equipment grounding conductor. Any comments, guys? Any questions about that? Any comments? Any questions? And we size it based on overcome protection device ahead of it. So that's what I thought just to share. I really appreciate any comments, guys, any correction about this sheet. I ran it twice. This is the second time we ran it. If you see anything that doesn't make sense, email me. I would love to update it and keep sharing it. I think it pulls a lot of things together. So you can use it like we are using it for a bigger system. Change this one, guys, into, like I said, instead 4,000, make it 400 amp panel, and make everything else like 100 or 60 amp or 200 amp panel. The same calculation applies. Smaller system, no paralleling, but I picked up the big sizes because they get you in the paralleling, which complicate things a little bit. Any comments, any questions, guys? So now what happens if your system is ungrounded? This is for a grounded system. Grounded service coming to you, grounded service. The almost we have an hour guys left in that one. The other hour guys, I have a couple pictures and PowerPoint presentation I want to share with you. But before we leave, I always like to say I started with delta Y. That's a grounded system, solidly grounded system. What happened if I started with delta delta? Feed the whole, not come in. You typically don't feed a building with a delta delta, but what happened if you have a delta delta? Everything that I told you, all this sheet applies. The only thing that you're going to lose right here if you have a delta delta is wherever you see a main bonding jumper or a system bonding jumper, these will be removed. That's all. So if the generator was a delta, or if the transformer was a delta delta, the separately derived transformer was delta delta, or if the service coming to the building was a delta delta, wherever there's a delta delta, you remove feeds the panel, you basically remove the main bonding jumper if it's a service, or the system bonding jumper if it's a separately derived system. Everything else stays the same sizing, no difference, no difference. And yeah, of course, neutral. Forgot to mention, if it's a delta delta, do you have a neutral? So all your neutral disappear, all your neutrals disappear, and of course, your main bonding jumper will disappear, and system bonding jumper if you're in the system bonding jumper side. The reason why I mention this one, guys, because the slides that we're going to go over is going to talk about grounding and bonding. Should I ground? Should I not ground? And the advantage and so forth. So what I thought, guys, just to start with this one, give you an overview of the whole sizing, and then we will flip. We will refer to it as needed. But I'm going to flip into here and talk about the fundamentals. So now we started with the complicated stuff. The reason why I do it this way, guys, because I need 16 hours to go over the book. We're summarizing 16 hours in 4 hours. So I thought, okay, should we start with a presentation like 2 hours that says, should I ground or shouldn't I ground? By the time we finish the answer of this presentation, guys, 2 hours are done. So I started with, well, 90% of the system that we use are grounded. But let's take a one big fat grounded system and analyze it from A to Z. So that's why I started with this sheet, just give you a big picture. And then the rest, I encourage you guys to go through the book. So I'm going to go over this one, starting with the fundamentals. General fundamentals to ground or not to ground, a couple of things. Here's what this chapter, guys, is. This book, it's a source book of on grounding. There are 22 chapters, I believe, in the book. These are just some of the stuff that I picked. So one chapter, guys, talk about the advantages of grounding over non-grounded system. We'll talk about this one. A grounding electrode system, we talked about this. Grounding electrode at the service, that's the bonding. And main bonding jumper, we have the grounding electrode systems here. That's a whole chapter about the grounding electrode system. A grounding electrode conductor, one more chapter. Bonding enclosure, that's equipment bonding jumper, a whole chapter about the equipment bonding jumper that we just talked about. Equipment grounding conductor, same thing. Enclosure and equipment grounding. A separately derived system, and grounding at a separate building. Each one of these is one chapter. I summarize almost all of them in that sheet that I told you. And I'm going to go quick, guys, and move around with these. I'm going to be picking and choosing about these. When you do, this is what my favorite. When you talk about grounding, first of all, before we start, 90% of the system that we use are grounded, right? Everybody knows you walk into a building, it's 480-277. I'm yet to see a building that's 480 only. Anybody have walked into a building that has service 480 only, like a Delta? Maybe center tap, 241/23 phase, but 480 only. Typically, guys, you need 480 strictly, and then they create new neutral if they need to. Okay, what the size?
Size of the service?
Yeah, if you remember. 1200, yeah. Okay. So, but typical manufacturing, typically if you need an ungrounded system, you start with a grounded system and then you create an ungrounded system internally. So if you have a factory on an assembly line, you got your 48277 that you can go distribute to get your lighting system. The key point is you get 48277, guys, it will burn all your lights at 277. So that's very efficient high voltage to burn equipment at. And then if you decided to use an ungrounded system for reliability, what do? You take a delta-delta transformer, separate to your system, and you run the assembly line on a delta-delta, if it's the situation. Okay, one of the most important things, guys, especially for the ones who have not been around for a while, that confuse me when I start talking about grounding is there are two very distinct things about grounding. Either you ground the system or you ground the equipment. And these are completely different things. If the system is grounded or ungrounded, meaning you take one of the guts, you go to the guts of the transformer and you take part of the windings and you ground it. That's grounding the system, the power system. Grounding the equipment, almost every system have to be grounded, meaning the enclosures of the transformers, the generators, these have to be tied to Mother Earth. So that's probably if you distinguish between grounding the equipment versus grounding a system. So we have systems, services, feeders, branch circuit, and equipment. So all these can be grounded or ungrounded. 99% of the time, guys, the system is grounded. One thing, if you guys, especially the electronic guys, electronic equipment and limited energy system grounding and bonding, there's a really nice chapter about this one. Unfortunately, we don't really do a lot of stuff, especially the electronic equipment. There is a whole different grounding and bonding, guys, for data centers. If you see a data centers, all these racks, you bond them, you'll see 4-aught going and tying all these racks together, and all the backbone of the grounding system. That's completely different than what the code is required. That's strictly for protection of the electronic equipment. That's strictly for the protection of the electronic equipment. So above and beyond what the NDC code book when it comes to grounding and bonding. So if you go to a data center and you find conductors that's 4-aught tying things together and going all the way to the service, that I can't remember. I never remember the requirement. There's a standard that you have to meet in order to get even the people to insure you in your data equipment, because there's the servers. You have to meet certain standards. Part of it is to create that robust grounding and bonding system in your data center. Anybody deal with that? Anyway, I do have a PowerPoint presentation about it, but if anybody's interested, it's interesting. Again, and also lightning protection, guys. Like that's why I said you walk into a building and you find them bonding and grounding with 500 kcm, because they take into consideration a whole lot than just the electrical system. The lightning system is a big protection tying it together, and the low voltage system as well. So I'm going to move through these, guys. This is just talks about why do we care about grounding and bonding. I always, when I teach electrical, I always summarize. I said, in order for the electrical power to work, all what you need is just one hot on a grounded system and Mother Earth at the end, right? So take 120 to your backyard with one wire, tie that wire to one end of a bulb with a socket, and from the other end tie it to a ground, like any metal object stuck in the ground, and tie it to it. In Minnesota at this time, you probably will get full bright out of that bulb. Anybody tried that one? So you're running basically as Mother Earth you return. That's no problem. The system will work. What's problem with this system? Number one is not efficient. Number two is not safe, obviously. So the smarter than Chad. So all what we really need is just one wire and the return of the system through Mother Earth. So to make the system efficient, they created another wire, so that got you the neutral. And to make it safe, they added a third wire so they can tie to all the metallic objects. In case any of these ungrounded conductors accidentally touch these metallic objects, that will be a disaster waiting to happen. So if you have a third conductor that you can pull all these, tie all these metallic objects, tie them to the ground rod, the overcome protection device will be able to trip. So this is just a few things, guys, about the basics and the safety. They call the grounding and bonding the safety circuit term interesting. This is just to emphasize what happened to the current as the resistor decrease. The resistance of the circuit decrease. You guys know that one. As the resistance of the circuit decrease, the current goes up. Who cares? If you have a ground fault in any system, the grounding and bond, really the main reason why we ground and bond the system is for safety. The main reason. Safety as safety from, you know, when you guys deal with 70E, there's two hazards involved from the science of electricity. There's the touch hazard, electrocution, and the arc flash hazard, right? That's really the two hazards. So when you ground and bond the system, you minimize both hazards. You minimize the possibility that people accidentally getting in touch with an energized object. If you ground and bond, circuit breaker will immediately pick that an object got accidentally energized, the fridge frame is energized, bam, trip fast. And number two, guys, if you have a ground fault, if the grounding electrode system is supposed to facilitate the flow of the current back to the source so fast that the circuit breaker will trip fast enough to eliminate the possibility of arcing and sparking and burning your building. So anyway, so the job of a grounding system then is to minimize all these conductors that I bombard you guys with, is to get you a very low impedance back to the source. Source is the transformer or the generator that generated that voltage. Back to the source fast enough before you create a fire or kill somebody. Is that a novel idea to do? Or otherwise, you can use barbed wire to carry current and not a big deal. This is just a few things, guys, to emphasize that current take all paths, not just the easy path. We always say the easy path. So if you have 100 amp current going here, and this is really nice copper, and this is the coax, the shield of the coax. So most of it will go here, but this will also be carrying current. So just to emphasize, why don't we bond at, like when we talk about bonding the neutral second building, why don't we do that? Who cares? Because your neutral current under normal operating condition will be going through your pipe system. Do you want this to happen? You don't want this one to happen. Okay, so it talks about, guys, grounding and bonding. Here's a very, very important concept. Here's my service. Right here is bonding the service, grounding the service. You can see it's solidly grounded to Mother Earth. Then you get into the building. The same thing we do. What do we do? Inside our building, we bond to our building. Do we really, why can't we just depend on this, right, to ground and bond our system? I always say people don't understand or miss it. So what happened if this conductor, well, in this case, it doesn't matter really, because what happened if you lose a neutral? In a case like this single phase, well, the power will go off, Chad, no problem. But if you have a 241-20 split phase power system like we all do, you lose a neutral, you burn homes. If you're not bonded to the neutral, you're bonded to the ground, literally. So that's where we take, guys, we go to your neutral, bond it to the ground. Now you stabilize the voltage and you minimize the possibility that a loose neutral will burn your building. And then you bond to the enclosure. I don't know if you guys can see right in here. The code requires you to bond the neutral to your enclosure. The neutral to your enclosure. Right. This is at the service. You go downstream here. The only thing you can see is isolation of the neutral. It's not bonded to anything else. And so isolation of your neutral and not bonded to anything else. So the current's supposed to return to its source. So if we, let's say, so we have a bonding jumper here, the ground. So if you have, I think there's an example where if we have a short circuit, here you go. What happens if you have a ground fault? A ground fault right here, guys. The current will, you can see this is a lot of current here coming. Now we faulted to the frame of that equipment. It's going to have a free ride over your rigid or EMT conduit because we don't have an equipment ground conductor all the way up to this point. That's where I want you guys to pay attention. Right here. This is where it jumps from the conduit to the neutral. This is probably, I don't know how many of you have paid attention to that one. Your ground fault current right inside the service, have a free ride over your main bonding jumper, here, um, and go through the neutral. I don't know if you guys can see, it jumps in here and it goes to the source. So now if this is grounded and bonded properly, you could, two things: minimize the shock hazard because it trips fast. Number two, also minimize the arc flash hazard, which could burn your building or kill people. Does that make sense, guys? So I hope you understand. I gave you the big picture because we could get stuck with all these for a long time before you even reach the whole big picture, guys. Okay, so normal operating current, the current goes from the hot to the neutral, no problem. Under short circuit condition, look what happened. So here's normal operating condition, hot through neutral back to the source. We have a ground fault. Now we go through the equipment to the equipment ground conductor back to to the source. What you need the overcome protection device, guys, to be able to see this. The second segment of this class will be about the overcome protection device. I'll show you how the overcome protection device will see this amount of, look at this one, 250 amp coming out of 20 amp. How would that happen? That's for a very, very short amount of time, less than 3 cycles. Then it will see it will trip less than 3 cycles, and by doing that, it prevents your building from burning and your people from being electrocuted. Any comments, guys? Any questions about that? Make sense? No, yes? So, a couple of definitions. They define the ground as earth, and grounded, intentionally connected to the ground, and bonded, connected to establish electrical continuity. So the reason why we bond things, guys, to put them at the same potential, so you're not standing here holding on a tag that's sitting at 480, and the other hand is holding on another tag that's sitting at 0 volt. What happens if you have a tag that got energized, the frame of it, and is sitting at 240, and you are sitting here, the other hand is sitting at 0. To get the current to flow, guys, all what you need is just a potential difference. If you have a potential difference and somebody to connect between these potential difference, you've got yourself a cooking process. So we bond to put everything at the same 0 potential, so no current can flow from 0 to 0. Microcurrents can, but no killing current can go from 0 to 0. Now you put 0 to 120 to 0, and you tie them together to a load. Now you got yourself a current. With current comes energy. With energy can burn and kill. So bond to put them at the same potential, ground to facilitate the operation of the overcome protection device. Okay, this is just a couple of things, guys, about the grounded conductor. We calculated why do we have the grounded conductor. The job of the grounded conductor in a grounded system is to take the unbalanced load of all the 3 phases or the 2 hots back to the source. That's the job of under normal operating conditions. So it's a current carrying conductor. Under normal operating condition, the neutral will be carrying current, right? The unbalanced. Okay, not permitted to use the grounded conductor. So the grounded, can I use the neutral to ground the building? First of all, would it work if you use the neutral to ground the equipment? Yes, no problem. It would work. Why wouldn't we use it? Then because the equipment under normal operating conditions should not be carrying current. If you ground them through the neutral, then you take a chance that under normal operating condition your equipment could be carrying current. So they used to do it with the dryers and ranges in the past, right? You ground the frame, no longer allowed. On the we'll talk about this one on the lawn side. Facilitate the operation of overcome protection device. So the equipment grounding conductor, guys, is really the most important thing I highlighted right in here. Why do we have an equipment grounding conductor? Facilitate the operation of the overcome protection device. You need a conductor that's large enough that can handle the ground fault long enough to trip the circuit breaker. Why? To eliminate that shock hazard and also eliminate the arc and the arc flash hazard. The grounded conductor, like I said, the grounded conductor's job is to carry the unbalanced load to the source. The equipment grounded conductor under an abnormal condition to carry the ground fault back to the source. Purpose of grounding. Why do you ground the system versus ungrounded? So back to the basics. When you have a grounded system, guys, limit the voltage due to lightning and surge. Stabilize. So I always say, what's the disadvantage of a delta? We have a delta ungrounded system. Delta, guys, if you have a surge, a lot of surge, volt surges in a delta can create, or ground fault can create a big surge in the voltage and burn electronic equipment. A surge in the voltage on a delta is not as easily absorbed as in a Y, grounded Y. So that's why we'll talk about the advantage and disadvantages of a grounded system or ungrounded system. Let's get into it now. If you have a grounded system, guys, the advantages of a grounded system is you have two voltages, almost always, 280, 120, 240. So you have two levels of things to work with. That's a big advantage. Burn these at 277, air handling unit at 480. Okay, so that's check. Second, stabilize the voltage to the ground. Now I have a 277 stable because I'm bonding it to the ground. It doesn't depend on what happened on the conductor that's coming from the utility because it's already bonded to the ground. And also, if you have any surges in the system, if your system is grounded, it can handle these surges much higher than if your system is ungrounded. What's the problem with the grounded system? If you have a ground fault in this fixture right now, it will trip the branch, hopefully just the branch circuit feeding it. So if you have a ground fault in the air handling unit in one ground fault, it will trip the whole air handling unit. So that's the disadvantages. Advantages of ungrounded system, guys, is assembly line. Talk about assembly line. You get that power through the assembly line. The first ground fault, the first hit, you're still standing. You get another ground fault on a different phase. Now you're down. Who cares if you're a manager and you're counting dollars and you're guaranteed one chance, and then you can monitor if you have a ground fault. You can say, great, now I can have any ground fault in my facility, and my facility is still making whatever it's making. So it's good for reliability. Disadvantage, guys, of course, is especially with VFDs, it burns a lot of VFDs. I heard now a lot of people, guys, are going not a whole lot impedance grounded system, which is the best of both worlds. Where you, instead of solidly grounded or ungrounded, either on or off, basically, the ground. So you use an impedance. So by having the impedance, you have the advantages of grounded system, and also you can control the flow of the current in that impedance. Then you have the advantages of the ungrounded system. You don't have to trip. If you have an impedance grounded, you don't have to trip. You can control this so you don't trip. You monitor it, you control it, you don't trip. And you can, and if there's any surge in the system, you absorb it through that impedance. So that's a couple of things. Here's a couple of connectors, guys, grounded. You can see all this conductive body extend the ground connection. So it always talks, guys, about grounded system connected to a ground or some conductive body that extends to the ground. You can see all these areas here. Extending the ground. Here's my ground right here, but by bonding it to the neutral and bringing it and also tying it here, I'm extending it, my ground, through the whole building. So all these, everything is tied to the same ground, and by bonding in my building, I have an alternative source. Can you guys see now through the ground we're tied together? Yes, it's not the best conductive method through the ground, but it's an alternative though upon the loss of your neutral. It's a safe could be a safe alternative upon the loss of your neutral. Okay, so here's your grounding. You can see where the connection of your grounding. Bonding, you can see bonding in the power system typically related, guys, to conduits and also bonding the equipment. So here's my equipment here, my system bonding jumper right in here. Equipment here, this conductor, the equipment grounding conductor can act as an equipment grounding conductor and bonding conductor because it bond the frame of the motor into the switch gear. So here's my bonding also here for this building. Any comments, guys? Any questions about? And can a conductor act as a bonding conductor and equipment grounding conductor? Yes. Look at the conduits, EMT conduit. EMT conduit, when you have the right connections, it can bond itself from both sides and act as an equipment grounding conductor. So it doesn't have to be either or. Yes, sir. No problem. No problem. Advise if you are outside for lightning. Yeah, so you drive a ground rod here, and you tie the ground rod obviously to the equipment grounding conductor. Yeah, they do it if you have a machine outdoor for lightning. They drive a ground rod right through it. Yeah, but you're not tying the neutral to it though. Yeah, you're just the frame. You can have a ground rod everywhere you want. Every sub panel you can have a ground rod tied to every sub panel. There's no problem as long as you don't bond a neutral to it. You know. Yes, sir.
For many years, you had to have your lightning grounds separated, like a few feet from equipment grounds. Kind of kick that a little bit with stuff that lightning that much could kick back into your system house. So, I mean, it was a price of a big change because
Yeah.
try to have those distances to have lightning rods and so now they're all bonded together.
Yeah, what is it, 6 feet or flash over it, flash to it? Right now, the code requires you to bond to every grounding electrode system, including the lightning. I guess if you have a lightning, a huge energy, suppose lightning, and I'm not an expert in lightning, but I know a few. Lightning is unlike the ground fault is going to go to the transformer. Lightning typically goes through the ground. But if you get a good hit close to your equipment, you probably will burn equipment. I don't know if because they're tied together, the current will go into your electrical system. I'm not sure if that's true, but I've never researched it because I believe it doesn't happen. Otherwise, the NEC code book will say separate them. It doesn't seem to be an issue. Yeah. Yeah. Yeah, if that's to happen, I assume the NEC code book will say separate them, but you create more hazard then when you separate them. You know, so yeah, yeah, yeah. So you have a okay, grounding compared to bonding. So you can see, guys, here's bonding the conduits. I'm not going to get into the whole issue, guys, but I want to summarize it with one thing. You bond to put things at the same potential. You ground to facilitate the operation of the overconduction device. A bonding conductor can act as a grounding conductor, and a grounding conductor or conduit can act as a bonding. So it goes both ways. They do the same function. Yeah. A bonding conductor can do the job of a equipment grounding conductor. An equipment grounding conductor can do the job of a bonding conductor. Oh, yeah. You bond to put things at the same potential, meaning, you put them at the same voltage, same potential, typically zero. You put them at zero potential, but you ground to facilitate the operation of the overconduction device. But there is a cross in between the two functions. So it makes a lot of sense, guys. If you have a big metallic object here and a circuit coming to it, anything metallic in a building have to be bonded. A good example is the grid here. The grid we have the light is sitting in the grid. Could the grid be energized through the light? Yeah. So the grid have to be bonded somehow to the electrical system. It's not an electrical object, but it could be energized through the light. So you have to bond your grid in the building to the grounding electrode system inside your building. Why? Because if it's the grid is to touch the hot, now everything line here will be 120. Imagine the hazard that can create. So that's clearly bonding. Grounding, the lighting fixture that you see right here has an equipment grounding conductor, because if the frame of that lighting fixture to become energized, that will tie to it, will get the circuit breaker to trip fast enough to eliminate the shock hazard. A couple of things, guys, about the safety circuit with the equipment grounding: continuous, have enough fault current. I'm going to refer to this one at the end in the afternoon, guys. It's not enough to have an equipment grounding conductor. It has to be fat enough to handle the handle the ground fault. And with the fat enough, has to be also big enough and low enough impedance to facilitate the flow of the current. Grounded neutral conductor. Oops, oh good, that one. Okay, we'll get that one. This is just I'm going to jump fast through that one. This is why we should not connect, guys, the neutral downstream. A lot of pictures to explain why shouldn't you connect the neutral downstream. Look at the current is going properly. Now I want to bring to your attention, if you are bonding the neutral here, here's the neutral is bonded here, and if you bond the neutral in this here, and if you bond the neutral right here to the boxes, so this is current circulate on all paths available. So you have if you do that when you bond them, can you guys see that bonding that they did here? Now the conduit is carrying current. Can you guys see that? And yes, sir. Yes, all these are from source book. All these pictures are from source book. So this is justification why we shouldn't bond downstream. And I'm sure you guys probably know that one. Okay, the only thing, this is, guys, from the NEC code book, and if you have been there, it's divided into all these sections. System grounding, and then direct DC. I'm not going to talk about the DC or these. These are specialty, guys, for the high voltage. Other than that one, guys, the sheet that I gave you covered every one of these chapters. Other than the DC and the instrumentation too, that's another one that the sheet did not cover. Other than these three, the sheet that I showed you covered all this stuff, the information that we covered. A few things about DC grounding, guys. You ground based on the largest positive or negative conductor in your system. So really not a whole lot, and you have to tie the positively grounded or negatively grounded system photovoltaic into your grounding electrode system of your building. Typically they do it through, you have to have through a fuse, because they have to monitor the ground fault. If you have a high voltage, higher than 600 volt, the code, if you go read it, it's exactly, they refer you exactly to the same tables that we did for low voltage. Exactly the same tables, 250.66 and 250.122. So really the same for high voltage, the same requirement in the code. Now, obviously, if you're doing substation, they have a ground grid that they use and a bunch of other things. So I'm just going to jump through, guys, these. So circuit conductor type, size, required, permitted, not permitted. The code talks a lot about which one need to be grounded, which one not be grounded. I'm going to go to these because these are really interesting concept. So let's go to the ground fault here. So you can see if you have a ground fault, ground fundamentals. So if you have a ground fault, guys, this is an interesting picture. The picture is really cool. If you have a ground fault in the service, this is supposed to be the service, you can see that the big chunk of the load is going to go through the neutral. Very tiny amount of current will go to Mother Earth. I like this one because what happened if you lose the neutral? Especially if you have a storm, guys, and the ones who have single phase, 243 wires, you lost the neutral. If you lost the neutral, who are only, not the phases, on a system that's 240, 120 split phase system, or 208, 120, 208, 120, 480, 377. If you lose a neutral, that minor connection here could stabilize at least stabilize the voltage for you. It will stabilize the neutral for you, enough to not to burn the building. It's not approved, but it's kind of a safety factor that you can use. Now what they're saying, guys, if you don't ground here, then there will be high potential between this piece of equipment and this piece of equipment. If you live in an area, guys, where the transformer is 100 feet or 200 or 300 feet away from your house, not a whole lot of potential. If you live in an area where the transformer is, say, 1,000 feet or maybe 700 feet away from where your house is, you could develop enough potential to be hazardous. The utilities use this, a very, very nice example, guys, if you do for the high voltage. If this is the ground and this is my grounding conductor and this is my neutral, they bond it together here. As they move, the voltage between them start going up, 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 and different. So at a certain point, what the utilities do, guys, when they do the neutral, they bring the neutral and they bond it back to the earth here. And then it's start going up, up, and again, and then they bring it back, they bond it back. So long story short, on the high voltage side, like you go, say you go 2 miles, and then you find them doing, what do they do to the neutral? They tie the neutral to the ground again. Because the further away you go from bonding the neutral to the ground, further away, the more the voltage will develop between them. In the low voltage systems, you don't go miles inside a house or a building, so it's not a big deal. But that's kind of the concept where there could be a potential difference between these 2 points, enough to knock you. This is just why you shouldn't, why we should ground, guys. The lit through and all this good stuff. So everybody knows why we should ground the system, because instead of Mr. Gentleman here becoming my equipment grounding conductor, if I have an equipment grounding conductor right here, it will take care of it, right? Does it make sense? That one, so an equipment grounding conductor should eliminate the shock hazard directly and save lives. So that's basically the major purpose of the grounding. So the hazard, purpose of bonding, putting things at the same potential and also acting as the same grounding. For example, path, ungrounded system. Okay, this is an interesting. If you have an ungrounded system, we'll talk about the system, guys. If you have an ungrounded system, I want to bring to your attention, guys, this transformer here. Do you see anything in this transformer tied to the ground? No. What you're looking at is ungrounded system. You do the same thing. The only thing that's missing out of here, out of this panel, do you see anything neutral bar, anything tied? You still have to bond. Can you just see that little dot here? That's bonding the enclosure to the grounding electrode system. Still have to do that. The only thing you don't do is you don't bond the neutral to everything there, because there's no neutral. Why do we ground exactly the same way if our system is ungrounded? Because if you have a second ground fault, you need to be able to trip your circuit breakers. You need to be able to trip, like in this case. I know it's going to be a phase-to-phase and your circuit breaker will wake up, but you need to facilitate the operation of the overcome protection device if you are to have another ground fault on a different phase inside your building. This is just be electrically continuous, guys. So when you have an equipment ground conductor, you don't get it. We don't get into sizing it a lot. All what the NEC code book make it easier for us. All what you have to do is go to 250.122, and what's your overcome protection device? Here's the conductor that goes with it. And as long as you use this table, the conductor will do two things. Will facilitate the return of the current when you have a ground fault to the transformer, and will hold the ground fault long enough. It's not going to burn, basically, long enough for the circuit breaker to trip. And I'll talk about this when we talk about the overcome protection device today, guys. So grounded system. When you have a grounded system, guys, the electrical system is grounded. That's what, and the equipment is grounded and bonded. Um, so that's really the difference. If you have an ungrounded system, the system is ungrounded, right? Everybody knows kind of the difference. So we have a delta. Electrical system design. Okay, we'll get that one. Short circuit. This is just about the rating of the overcome detection devices, guys, and defining a short circuit. I'm going to move on to that one. So a short circuit is defined as any unintentional contact between any two ungrounded conductors or the grounded conductor. That's how they define it. So you have phase-to-phase short circuit. How about phase-to-ground? Ground fault. Do you guys see if you have a three-phase short circuit, do you see the ground, the equipment ground conductor, does it play a role? Does the equipment ground conductor play a role if you have a phase-to-phase? No. You wouldn't see the phase-to-phase. The phase-to-phase will sit on the two phases only, will be seen by the circuit breaker and trip. If it's phase-to-phase, same thing. The equipment ground conductor wouldn't see it. The only time the equipment ground conductor will see it if you have a phase to ground or a phase to phase to ground or a phase to phase to phase to ground. Now it's going to go back on the equipment ground conductor. Here's the ground fault. Ungrounded conductor of an electrical circuit and the normally enough. So they define it, guys, any hot touching any grounded object, any metallic object in the system is a ground fault. Any hot touching any metallic object is a ground fault. So that's your ground fault. So here's your ground fault. Your ground fault. Even the grounded conductor touching the so unintentional electric conductor connect between any ungrounded conductor of an electrical circuit and the normally non-carrying. Okay. So here's my two ground faults. How about this? Is this a ground fault? The neutral touching the ground. Is this a ground fault based on the definition though? Is it unintentional electrical conducting connection between an ungrounded conductor or of an electrical circuit and a normally non-carrying conductor? So a neutral to the ground is not a ground fault. It's not a ground fault. What's happened if you do that? A neutral to the ground. Now you got the, if that's to happen, it's not going to, nothing is going to trip except now this guy will be carrying current as well as the neutral back, right? So you go open the green conductor to work on it. You get zapped because it's carrying the unbalance between all these fixtures in this room. And other characteristics. This is I'll talk about the withstand rating of the conductors, guys, in the afternoon because that's with the overcome detection device. Selection and coordination, we'll talk about this one in the afternoon as well as the short circuit. That's really the topic of in the afternoon that we do. So a long story short, guys, when you have a ground fault, your equipment must be able to handle the ground fault and your circuit breaker must be able to handle the short circuit and the ground fault enough for circuit breakers to open. Your equipment have to be able to withstand the mechanical magnetic stress that's going to impose on them, the ground fault, and the heat from a ground fault or a short circuit, withstanding enough for the circuit breaker to trip. I'll talk about these. Let's talk about the ground path. Okay, with delta. Here's a very good example, guys, of grounding. I found it really nice. On A is looking at a grounded system. B is ungrounded system. Do you see any difference between? Can you guys see any difference between them? No neutral. Everything stays the same. No neutral. And because there is no neutral, no bonding the neutral to the ground, right? Because the neutral doesn't exist. Do you see any difference in the way we bond them though, or ground them? Exactly the same. No neutral. No neutral. Nothing. So that's my equipment. Now, can you guys see that this one is this one right here and this one right here? That was my equipment ground conductor in both sides, or bonding conductor. Okay, required to be grounded. A couple of things, guys. I want to what the NEC code book require a couple of systems to be grounded. I'm going to emphasize this one, because that's probably one of the most important ones that if you have them, you have to ground them. 50 volt to 1000 volt AC system, 1000 volt and over impedance systems. So if you have a high voltage, guys, system like higher than 1000 volt, it's up to you to bond it, unground it. It's optional. You ground, not bond it. Ground the system, the windings. You can run grounded or ungrounded. Impedance grounded, it's up to you also for certain system to run impedance grounded. Let's just go directly to the systems, guys, right here. Look at these systems. If I have a 50 volt for the low voltage, guys, if my system is less than 50 volt, but I'm feeding it from a 277 transformer, so you have to ground the system if it's fed from 277. Ungrounded supply, less than 50 volt. So these are all ungrounded system. These are what you're looking at. These system must be grounded on the system here must be grounded on the secondary side. Must be grounded. And this system here, if it's overhead, must be grounded. Anybody knows why if we put them overhead 50 volt, why would you use an overhead 50 volt outdoor? Cable TV? Good point. If you are to do that overhead, you have to ground it. Why do we ground it? Lightning. So these are the requirements if you have a system 50 volt or less than 50 volt that must be grounded. Must be grounded, the system. So that doesn't apply a lot to a lot of you. Here's what applies to a lot of us, guys. Okay, if you have a single phase system where the system can be grounded, so the maximum voltage to ground not exceed 150. This one, guys, will cover, I don't know, I've never seen a system 120 only. Anybody worked on a system 120 only? I'm sure they have. They used to use, and this is the most common system residential. So if you have a system, guys, 120, 240, single phase, 3 wire, this coming to a building to feed it, must be grounded. That's typical. The other thing is, guys, a Y. If you have a Y, you have to ground it too. And a delta center tab. Can you guys see if you have a delta center tab? 3 wire, if 3 phase, 4 wire. Why are you pulling 4 wire from a 3 phase system unless you need a neutral? Then you have to ground it. So that's the requirement for systems to be grounded. So systems, if it's over 1000 amp, guys, if it's feeding mobiles and portable equipment, you must ground them. So these are just the higher voltage that you must ground them. kVA over supplying portable equipment. This is must by code. If you're supplying portable or mobile equipment, you have to ground them. When you ground them, guys, you don't have to solidly ground them. You know, you can ground them solidly, or you can ground them through an impedance. So okay, so I'm going to go to electrical systems that are not separately derived system. This is just a few things about definition of separately derived system. If you guys look at the neutral, we created a neutral, and do we isolate it here? No, this is non-separately derived system. If you here, do we isolate the neutral here? Or the conductors on the primary side and the secondary side are isolated? No. So this is two good examples of a non-separately derived system. Pictures of a non-separately derived system. Let's go directly into permitted to be grounded. Okay. When you have a system is permitted to be ungrounded. This is really interesting. If you have a system, these are the systems. I like this one because it has a voltages, guys. Permitted to be ungrounded. So if you have a building, you can bring any of these ungrounded to your building. Do you see 208, 120 here? Do you see 480, 277 here? No. The only thing is 240. You don't even see 208. 208 is not here. 480, 2300, as well as the 46 and the higher voltages. These systems, guys, are permitted to be ungrounded. What does ungrounded means? Nothing from the transformer windings connected to the ground. From the transformer windings. If you have an ungrounded system, guys, what do you need? So here's the systems that can be ungrounded. If you have an ungrounded system, the code requires you guys to declare that your panel or your source of power is ungrounded. So if you have an apprentice walking in looking for a neutral, hopefully they will realize that you're looking for something that does not exist. Hopefully, when you see caution, ungrounded system operating at 240 volt between conductors. And then, so we talked about, guys, the systems that can be grounded, and the systems that, so imagine going through this one before you even reach the how to ground. This is how to ground. So these are the systems that must be grounded. You can see there are Y or center tap delta or split phase power system in the second. These are the system coming in here. These are the systems that can be ungrounded if you want to run an assembly line with them. Now these are the system circuit not permitted to be grounded, and you can see these are the ones that cranes above class 3 location hazard, right? Isolated power system in care facilities, and circuit for electrolytic cells. These shall not be permitted to be grounded. Not permitted to be grounded. You have to run them ungrounded system. Any question, guys? Any comments? How often do you deal with ungrounded system? Do you guys deal with them a lot? So that's why we spend the major bulk of the time talking about the grounded system. Otherwise, the code have a tendency of getting you lost in before you start sizing and what need to be grounded, what not need to be grounded. 90% of the system that we use, guys, need to be grounded. And the sheet that I gave you apply to them. The other 10% need to be ungrounded, and the sheet that you got also applies to them if you remove the neutral. If you unground the system, the code requires you guys to monitor the ground to the current to the ground and trip. So you have to have a monitoring system to be able to decide if you have a ground fault. So this is typically in the hospital. You monitor what your milliamps, and you can alarm or trip on a ground fault. So if you are to use an ungrounded system, you must have a way of monitoring the ground fault, that you have a ground fault. And it doesn't have to trip. You can monitor it, use it to trip, or use it to alarm. Here's a ground fault on an ungrounded system. It makes it corner grounded delta. Nothing will happen. Everything continues to work. Here's how they do it, guys. Monitoring an ungrounded system. If you have an ungrounded system, the easiest way, guys, is to tie them to a couple of resistors and a couple of lights. If you have a ground fault in phase A, the light tied to phase A will dim or go dead. So that's an indication. The better than that is you have a transformer. I don't know if you guys can see a transformer here that actually senses what's going on. The same thing, the light. If you have a ground fault in phase A, say this was phase A, can you guys see that this light went down or dead? And in a case like this one, I have, so you don't have to trip. It can send, it can give you an indication that go shut down the plant one day whenever, around Thanksgiving holiday, when you're not making anything and everybody wants to go home, shut down and check for your ground fault. If you guys go online and see Color Hammer, a bunch of other things, there are ground fault detectors that can actually analyze and send a signal and get you where the ground fault in your system is located to. So they have the more sophisticated than you can imagine, the ground faults. This is just a disclaimer, not disclaimer, but a declaration that every system is grounded, but how big of an impedance you are grounding it through. So you can see these are all actually, there will be a charging current going here through the air to the ground. This is true if you have a high voltage, guys, 600,000 volts. And so there will be a losses. I happen to be an engineer. We did transmission lines. When we do transmission lines, you bring the power from Becker to Minneapolis. As you analyze the power system, you indicated a capacitive impedance between your transmission line and the ground, and that capacitive impedance is taking current out of the system, and it will contribute to the lower voltage that you can see on your transmission line. So that's a big concept in the high voltage transmission distribution system. Not a whole lot in a 480 system or less. But there will be, if you go in the system that is ungrounded and you measure the voltage, you'll get a fluctuating voltage because there is a capacitive impedance that tie the phase to the ground, right? So the reason how this capacitive impedance happened to be, guys, keep in mind there is a conduit here, don't you think so? There is a conduit where all these conductors are in, right? So now what's a capacitor? A capacitor has a positive and a zero, right? So here's your positive is the hot, phase E or phase B or phase C, and what's the zero? The zero is the ground, is the conduit. So that's where capacitive inductance, they call it. So you could be zapped from an ungrounded system, get a shock, not as bad as a grounded system though, because of the capacitive impedance. Okay, disadvantages of ungrounded system, guys. Transient voltages is a killer. A lot of systems, guys, transient over voltages are not controlled. Over voltages are not controlled in the power system. System voltage above ground are not controlled. Potential arcing and location of the ground fault is difficult. Now with the technology is really not hard to do. That's ungrounded system. And that's basically it in terms of that one. Any comments, guys? Any questions? Any comments about the grounded system? So we have I want to show you quick. We have 20 minutes until to eat. Can you guys have energy for 20 minutes to show a few things before we flip? Let me show. I went fast through these because there's a lot of stuff, guys. Okay, so I went through that one. The second couple of chapters, guys, talk about grounding electrode systems and grounding electrode services. I want to just pick up. Here's an ungrounded system, guys. The disadvantage of the danger of the reason why the code wants you to measure the volt sense. What happens if you have a ground fault in this phase? Right? What's the voltage to ground? And this system happened to be 480. Right? If you have a delta ungrounded and you have a ground fault in one phase, what happened? Nothing will happen. But you have a ground, one phase grounded. The system continued to work. Now what's the voltage to ground now? 480. So imagine you're in a panel, you're working on a panel, and I read an article, guys. 85% of the faults in any system are ground faults. 85. How often do you take phase A and phase B and phase C, bolt them together and flip the switch? But how often do you drop something in a panel and you get an arc from that? Or you're working over there and your screwdriver touched the metal frame while you are tightening it if you're working hot as you're not supposed to. So 85% of the faults are ground faults. So you have a panel, the voltage to ground is 480. How dangerous that would be for a shock, from a shock hazard point of view? Typically what? 277 is the voltage to ground. You double the voltage to the ground. If you get a shock with a ground fault on a system, a delta system that's have a ground fault on it, you're dead. Your chances of surviving a 480 ground fault here is much less than if the voltage was 277. Anyway, so that's why the code wants you to do what? Monitor if you have a ground fault in your system. Not because we care about your process, because the shock hazard that comes from a higher voltage to ground Here's a couple of systems, guys, that we use that's grounded. A lot of people, guys, take a grounded system and they go ground it, an ungrounded system, and they ground it to stabilize it. What's the disadvantage of using a corner grounded system? If this was a 480 system, if that was a 480 system, now your voltage to ground is 480 at all times. So that's the major disadvantage. What's the advantage of it? It stabilizes the voltage to the ground for you, and it eliminates the over voltage problems that it creates in your system. A couple of neutral points, guys. Talks about the grounded conductor and neutral points. All these are neutral point. All these this is neutral point with a grounded conductor. This is a good reminder that every neutral is a grounded conductor, but not the other way around. For example, is this a neutral here? No, it is a grounded conductor though. So here's my neutral points and neutral conductors. Definition by the code. We talked about the sizes, guys, and the color coding. This is a couple of things about the color coding. We all know that the continuous white or continuous gray or 3 continuous white stripes, these are the way we define the grounded conductor. If it's number 6 or smaller, you go higher than number 6, you can use black, no problem, as long as you want. Put a white tape around it or a gray tape. So these are conductors. Grounded conductor different systems have to be separated, guys, and identified at the panel. If you have two voltage systems in your building, as most buildings do because of 480, 277, 208, 120, you're supposed to identify the color code for every system by phase and by in system. So you end up with the color coding for the 208 and the color coding for the 480. So solidly grounded, all of you guys are familiar with solidly grounded. That's where you get the Y. Then grounded through a surge arrestor. All these guys are reactance grounded. This is very common in high voltage where they use impedance. They call it impedance grounding, reactance or resistor, and they ground the system through it. Here's a couple of resistance, high resistance. High resistance, I want to resistance grounding. You have high resistance. Look at the amps here. Can allow only up to this amount of amps to go. If you, I'm sorry, the resistance grounding, the high resistance grounding limit the current even more. So now who cares? So this is what I said, like the best of both worlds is if you have a process, a manufacturing process, and you want your manufacturing process to work properly, probably the best option for you with VFDs and everything else is high impedance, or impedance grounding in general. Then you have a ground fault, no problem, bring it on. It doesn't trip, and if you have a transient in the voltage, the system is grounded, so it sucks all this transient, take it to the ground. So that's that. But with this, you have to alarm. Of course, you have monitoring system that alarm if you have a ground fault. Obviously, ungrounded system, you can see nothing here is tied to the ground. Nothing is tied to the ground. Any comments, guys, about solidly grounded system, impedance grounded system, and ungrounded system? 90, as I said, 90% of what you're probably dealing with, guys, is grounded, solidly grounded system. Ungrounded system and impedance grounded system make 80%, 10% probably of what we deal with. Why ungrounded? And if you can, the best, which one is the best if you have a manufacturing process? Impedance grounded. It gets the best of the grounded system and the ungrounded system. The survivability of the ungrounded system and the reliability of the ungrounded system plus the resilience of the grounded system. This is how to calculate the wild leg. And we all know that the wild leg have to be identified, have to be orange on phase B, right? All this good stuff. identified phase B on wherever you're pulling it, right? How many of you guys have burned a couple of equipments by pulling a phase B with a neutral and get you to it? So this is a few things that you know: sizing of existing ungrounded conductor systems. Okay, we'll talk about this one. Grounding delta bank with zigzag transformers. If you have an ungrounded system, guys, and you need a neutral. One method is to buy another transformer, delta Y. That will be a lot of solution. The easier is to buy a box that looks like really not a transformer, single winding transformer that's called zigzag transformer. What they do is they play with the magnetic field of all these coils to get you the 0 point. So the minute that you create the 0 point between all the phases, like you can see right here, guys, you create a neutral point, right? So what is a neutral point? You take phase A, phase B, phase C, add them vectorially, not algebraically, vectorially as vectors, add them vectorially, and when you add them up, if the system is balanced, what do you get? Big fat 0. So that's how they do that one. They create the 0 point, the neutral point. If you create a 0 point, polar wire, call it neutral. So that's how you can get a neutral on an ungrounded system, right? And you get your 277 lights or whatever. That would be a solution for an existing problem, not a good design for a new building. So here's your in neutral that coming out of your zigzag transformer to get you 277 out of 480 delta. Grounded delta banks. Okay, we got the 208. So that's just okay. Here's this is about sizing the grounded conductor, guys. We talk about how to size a grounded conductor for 90% of the times. What happens if you have a corner grounded delta like this? Phase B right here is a grounding conductor, but cannot be, in this case, less than any other phases of the system. So long story short, if this conductor was 4-aught, what do you think the grounding conductor here would be? It's a phase B. It has to be 4-aught. So anyway, so the code talks a lot about it, but this is probably one of the most confusing ones. Maybe the other. This is the most confusing. How many of you guys have seen a 3-phase system feeding a single phase panel to feed a 3-phase load? That's what you're looking at. Talk about goofy stuff. Now, isn't that a recipe for disaster when you send an apprentice there? You're looking at a single phase panel fed from a 3-phase system, right, to feed a 3-phase load or single phase load. So imagine sending somebody here, and you walk in there and you see a white coming in. What do you think this would be? Neutral. And you go pull, okay, let's still pull this one and pull one of the phases right here and go land this one on my lighting fixture here. Now you got yourself, typically these are 240 or 480, you got yourself 240 across a light that's rated for 120, you burned it. So, but it's legit, it's good, it meets the code. So, but it's not a good idea. If you do this, if you have a delta system, guys, your circuit breakers also have to be rated for delta circuit breakers, they call them. And somewhere here it says rated for. You cannot use a slash voltage for it, basically. So here you go. So right here the type is 240. So 240 line to line or 240 line to ground. Doesn't matter here, you know. 240, I think we have, there you go, the 240 right in here, to type 240. But you cannot use this one. Anybody knows why we can't use this one on a delta corner grounded? What's the voltage to the ground? 240. What's the voltage to the ground? That's this circuit. It's 120. You're exceeding the voltage rating of this circuit breaker. So they call them delta rated circuit breakers, 240 only. Okay, so that's that one. We talked about all this, guys. I summarized all this one for the grounding conductor for you when we sized it. Here's just a couple of interesting things how you bond the neutral right here. See, bond it to the enclosure. That bar here is bonding the enclosure of the disconnect to the neutral, to the grounding electrode system, and to the equipment grounding system too. Can you guys see the green is equipment grounding system? That guy is a grounding electrode system. The white is the neutral system, and the enclosure. All of them are bonded right where Mr. Disconnect reside. You're supposed to bond them right at the location of the disconnect, service disconnect. This is allowing you guys, and it has to be for every disconnect, with one exception. If you have a switch gear like this, you can bond them right at the bottom of the switch gear because they're all listed together. Otherwise, you have to bring the neutral to each and every one of these. So what they do is they put they bond the neutral and the ground at the bottom here because it's a listed equipment based on an NEC code book. 250.24b exception number 1. I'll show you. So we have an example. So grounding, we talked about these. So what they're saying, guys, if you have, we do this all the time. You bring a gutter and you bring your service conductors and you tab them and you go from one disconnect to another. The code require you to bring the neutral to every disconnect and bond it to the enclosure of every disconnect. That's yes, we're talking about service. Yep, absolutely. So where these are all service. Very, very important. Now, can I bond the neutral to the enclosure right here so I can bond it? You can. There's nothing. This is the line side. I can bond as many times on the line side as I need without creating redundancy in the paths of the neutral current. So here's my typically service connection to be accessible. So they ask about the service connection to be accessible, guys. What you do is you ground right where your disconnect is located, and you bring your equipment grounding electrode conductor to the location. This is typically the location where you bring your equipment ground conductor to the location where you bond the enclosure and the neutral. Okay, size of the grounded service conductor. We talked about the sizing, guys. Talked about all these dwellings. Talk about the all service. This just talks about all the sizes that we showed you guys. Metallic, non-metallic, underground. So, okay, so high impedance grounded. Okay, if you have a high impedance grounded, this is interesting because we didn't talk about it. Here's a requirement that you need to do, guys, to maintain. You have to have a qualified. I can't have high impedance ground. I have 5 minutes left. Yeah, I can't have high impedance ground in my house, even if I want to. I can't. So you have to have the qualified person. Continuity of the power is necessary. You have to have some type of detection, and there is no neutral load. These are the conditions that if it's met, you are allowed to use a high impedance ground, right? Or ungrounded system, as a matter of fact. Here's how they do it. You put your 1 to 10 amps, or what is it, 200 to 600 amp resistor rated here, and that will limit the current in this neutral conductor to 10 amps or 600 amps, depending on what type of resistor you do. And you monitor that, and you monitor the current here, and you alarm upon the existence of a ground fault. What's the disadvantage of this? Exactly like the ungrounded system, I cannot tie anything to the neutral. There's nothing, you can't tie anything to the neutral. I want to, can you guys see how it's always amazing, make the people confused, is how it's coming from here all the way to the ground. It has to be in series between the Y, the center of the Y, and the ground, in series, not in parallel, in series. Can you guys see that? It's going directly in series. Here's a couple of applications where you have impedance grounded system. Okay, let's go eat. I'm going to show you a couple of things when we come from lunch, guys, and then we'll. I know it's